facilities, all located in the US, with a complete line of product as well as engineering services. This slide is just to give you an overview of the 24 countries SEL currently operates in, which is indicated by the blue areas. I'll just touch briefly on what a microgrid is before moving on to what SEL's microgrid control system is about. The term microgrid can be defined in many ways, but in a nutshell, a microgrid consists of firstly, a group of localized distributed energy resources and loads, and secondly, it is normally connected to a traditional centralized grid, but can also disconnect and operate in an islanded mode. This is possible as a microgrid can generate, distribute, and regulate the supply of electricity to customers locally, just on a much smaller scale compared to a centralized grid. Even though a microgrid can function autonomously, some interface with the bulk electric power system is still required, and this is done by various methods depending on the microgrid system design and local energy regulatory requirements. Every microgrid is unique, and on this slide you can see an example of the community microgrid highlighting several DERs and its associated critical loads, which has a single point of common coupling for connection with the energy power system. DERs includes photovoltaic or solar and wind resources to supplement existing load and demand, which can also be used to charge storage systems such as batteries that form part of the microgrid for future use. Finally, in this slide, there's also dispatchable generations in the form of a diesel generator. I've used this example as it shows both conventional and inverter-based DERs being used. On this slide, we look at some of the benefits that the microgrid can deliver, such as optimizing grid efficiency, improving grid resilience, and reducing emissions. Also, benefits such as reducing operating costs and minimizing demand charges are very valuable in any industry, what more in the industry of power, where cost is everything. Now that we've touched on what a microgrid is, let us move on to what SEL's microgrid solution usually looks like. So what is SEL's microgrid control system? Well, SEL's microgrid control system consists of several features that form our solution, with some of the key features being a HMI SCADA package for visualization, islanding detection and decoupling schemes, load shedding, DER optimization with economic dispatch, as well as auto-synchronization systems at the point of common coupling. Let us now look at SEL's microgrid control system sequence and how it works to maintain grid stability, which is a key component for any microgrid system. A microgrid control system maintains system stability both during grid-connected operation and during islanded operation. The two important components of SEL's microgrid control system are the controller and the relay at the point of common coupling. A typical operational sequence of SEL's microgrid control system can be explained as follows. This example assumes the system is connected to a local utility, which is the main grid to begin with, and that the microgrid is operating in a grid-tight condition. Once the relay detects an islanding sequence, which can be unintentional or intentional, but for this example, let us just assume it is an unintentional for the worst case scenario consideration. Once the islanding sequence is detected, this is closely followed by the SEL microgrid controller stabilizing the power system in an islanded mode of operation through actions such as load shedding, generation control, or DER optimization. This is then further followed by reconnection or auto-synchronization when the local grid is stabilized, which eventuates in the system reconnecting to the local grid. This is the general sequence of operation of SEL's microgrid control system. Each microgrid is unique in terms of available system objectives and other system-specific parameters and capabilities. At SEL, we customize our microgrid solutions to match customer needs and requirements, and usually classify our offerings in two general tiers. Tier 1 is a simple relay-based microgrid control system, and Tier 2 is a centralized controller-based microgrid system. Let us have a quick review of both of them now. A small distributed microgrid with few critical loads can be accomplished by a simple relay-based scheme. An example may be a relay at the point of common coupling, or other dedicated relays in the system, such as the SEL487E as depicted in this diagram of this small microgrid power system that can perform controls on top of metering and protection functions. Distributed microgrid controls being performed in protective relays is practical because smaller microgrids require less complicated controls, fewer features, less communication, and less data storage. A mid-scale to a large-scale microgrid relies on tracking several parameters. It usually uses a microgrid controller at the center of the architecture as shown on this slide, because it makes the decisions based on user inputs and priorities, as well as the topology of the power system it is trying to control. It is imperative for the controller to have timestamp data so that it can make real-time decisions, coordinate devices, and perform sequence of events reporting. It is important that the microgrid controller be supplied with accurate data from the intelligent electronic devices, which is depicted here by the SL2440, Axions, and SEL735 and 751. The data from the IDs are sent to the microgrid controller via the communications interface, which includes an Ethernet switch, which is depicted again by the SEL2740S, and other communication circuits. As previously mentioned, there are two tiers of microgrid offerings that SEL provide. And for our Tier 2 solutions that have a controller, SEL uses an SEL3555 real-time automation controller, which is a protection class substation hardened equipment with extended temperature range, shock resistance, electromagnetic immunity, and static discharge capabilities. The SEL3555 provides many features that make it a robust choice for a microgrid controller. It has an embedded Linux operating system, multi-thread processing, embedded security, and no moving parts as part of its hardware build. It also has software and communication protocols such as IEC 61850, GMP3, and Modbus that allows it to communicate with a wide variety of IDs that form part of a microgrid system. Now let's delve a little bit into the economic dispatch engine that SEL provides as part of its microgrid controller solution. A power system is a combination of energy sources and loads. The RTAG with economic dispatch library allows operators to see the relationship between the cost of operation and energy source selections. Energy sources have a variety of factors that influence availability and costs, such as weather, tariffs, output efficiency, and fuel prices. Using historical data and weather forecasts, the RTAG Economic Dispatch Library forecasts load profiles and optimizes the utilization of multiple energy sources to maximize return on investment, as well as minimize operations costs. Next, let's look at how SEL differentiates itself with the competition through its testing of all its power management systems and microgrid systems using something called hardware in the loop testing. One of the unique capabilities of SEL is the real-time digital simulator, RTDS, it uses for system testing. The ability to use hardware in loop testing during the design and testing phase results in less field work, which leads to shorter commissioning timelines. Depending on the size and application of the configuration, there may be hundreds of scenarios, both economic and operational, of varying complexity. The hardware in the loop testing is capable of performing all of these functions. Many timelines associated with microgrids are very tight, So the fact that SEL is able to ship a system to the field that has been properly modeled and configured takes a lot of risk out of the overall microgrid solution. This is a key feature that the competition does not have. Now that we've gone through SEL's microgrid control system, what microgrid control system is about, let us review some of the market credentials that make SEL the leader in the microgrid solutions, as well as the various projects SEL has completed up to now in the microgrid space. Let's first look at the Navigon research report conducted in 2018, which is a third-party report to examine the strategy and execution of 15 leading microgrid control vendors against 12 key criteria, with some of them covering each vendor's go-to-market strategy, innovation, product performance such as seamless islanding, and controls functionality, to name a few. From this, Navigon Research came up with a leaderboard methodology which profiled, rated, and ranked vendors with the goal of providing industry participants with an objective assessment of these companies' relative strengths and weaknesses in the global microgrid controls market. And as you can see, SEL was ranked as one of the leaders in this field. Another success story for SEL was when its engineers partnered with the Department of Energy and MIT to build a mock microgrid called the Banshee microgrid system. This was created to assess distributed energy resources and microgrid control system technology, as well as develop and analyze several test cases and use cases that serves both economic optimization and grid resiliency. The US Department of Energy Office of Electricity Delivery and Energy Reliability sponsored the project model. The goal of this symposium was to showcase to the participant, which included companies from the utilities, individual power producers, and other microgrid customers, the concepts of a control system, and showcase the effects of grid resiliency and the role of economic optimization microgrids can play in the modern power grid operations. This slide shows a picture of SEL participating in the first stage of the MIT symposium, which was also participated by a few different companies. In the center here, you can see the SEL microgrid control system controller, which is the SEL3555 RTEC, which I mentioned earlier, with a digital I/O and 2 points of common coupling relays being used as part of this test bed. Following this symposium, the US Department of Energy's National Renewable Energy Laboratory, NREL, invited 5 microgrid controller manufacturers to participate in a rigorous 21-week evaluation to determine the best controller for the energy systems integration facility. It was a tough evaluation in which the 5 manufacturers were evaluated based on the following key points: power, hardware, and the loop device validation, cyber physical test bed, economic optimization, adaptive protection schemes, and a couple of key performance parameters. SEL passed the evaluation stages successfully and came out as the winner, which resulted in the purchase and installation of SEL's microgrid system at NREL's facilities, enabling research capabilities to more effectively evaluate microgrid systems and their components. Moving on, we will go through a couple of projects that SEL has successfully delivered to date. This is St. Paul Island, which is located in the Bering Sea. A centralized microgrid control system was implemented to assist effective operation of the wind turbines and diesel engines coupled to the flywheel electrical storage component. The wind turbines have sufficient capacity to support the entire island without using the diesel engines, allowing the formation of an islanded power system completely powered by renewables. The proposed strategy includes use of the flywheel, wind turbines, and diesel generators to attain survivability and resilience. Then there is the University of California, San Diego project, which is a flagship microgrid system in the US, started in the wake of the 2011 Southwest blackout. When the power outage disrupted critical operations, campus officials recognized the need for an islanded system in which SEL delivered a solution. This slide shows an example of the single line diagram of the implemented microgrid system for the University of California, San Diego, just to give you an idea of how the power network looked like. Finally, here on the slide, we have a list of reference projects that SEL has completed as part of its microgrid solutions. And for any additional resources we have on SEL microgrid solutions that you might be interested, these are the links that will allow you to access some of our papers and videos pertaining to microgrids. So that's all for my delivery. I just want to thank everyone for listening, and I hope it was informative. And I look forward to speaking to Sarawak Energy, as they mentioned, hopefully on collaborating on some solutions. Thank you.
Thank you, Mr. Mohan, for your presentation. And for Q&A, is there any question from audience? You can put your question in the chat box. Okay, let me ask you, Mr. Mohan, from the system that you present just now, resources, which part is the most challenging?
I believe, obviously, one of the most challenging aspects of coming up with a microgrid solution is obviously understanding the system requirements of a customer, having to sit down with them to understand what are the generation sources, how the energy networks will look like, to allow us to create our, I would say, logic within our controller to meet the requirements. And usually what we do is we work with them to come up with the design, and we do something like I mentioned, hardware in the loop testing to prove this concept before going to site and implementing the solution.
Okay, thank you again, Mr. Mohan. Very informative presentation, Mr. Paul. Thank you again. Now we would like to back to the next presenter.
Thank you very much.
Thank you very much.
All right, thank you everyone.
Thank you, Mr. Now we proceed for the Mr. O Tianfu, the General Director of Vision International. Let me introduce Mr. O. Mr. Wotian is responsible to engage and help users in Asia Pacific to achieve top quartile government through digital transformation and artificial intelligence plus Internet AIoT solutions. He is a top leader in Industry 4.0 and speaker in many conferences regionally. He has vast experience in the process automation industry. He started his career as control engineer in process plant since 2003 and will move on to become solution providers. His experience includes project execution, proactive maintenance, and smart operation. Prior to joining Vision, he is a director of industrial IoT solution in Amazon, covering Asia Pacific region. He has been piloting digitalization and IoT projects since 2012 and has implemented several key projects across Asia Pacific. In recent years, he is active in the area of smart energy. Without further ado, we can the question to Mr. O. Present his presentation.
Hello, good morning. Thank you, host and the chairman. I just wonder how can I share my screen here?
I already assigned you to presenter, so you can go to the button of the screen. There is a share.
Okay, let me try. Yeah, I still do not see the button.
Okay.
Yeah, I don't the button for sharing is still gray out. I cannot share.
Yeah, I try to. Wait a minute, we try to.
Sure.
Wait a minute, Mr. Sorry.
No problem. I hope you can hear me correctly and
I
see
can
me
hear
correctly.
you. I can hear you. Yeah. Presente. Now, present. Jadi kan present share. Present ini. Yes. Mr. Wong, could you
Yep.
share your slide now? Okay.
I still cannot. I don't know why the share button is not available here. It is there, but it is gray out. I cannot click.
Okay, great.
Shall I just maybe exit and come back again? Let me try that.
Oh,
Okay, I just went out and come back again.
So
Okay.
can you try again
Can
now?
you try again?
Oh yeah. Now it is okay. Can you see my screen now?
Okay. Yes.
Sorry for some technical problem.
All right. So, Mr. Host, shall I begin?
Yes. You can start.
All right. First and foremost, sorry for all the technical glitch. Today, I would like to talk about how to solve the DER challenges through the digital AIoT way. And we believe that today, the digital way is one of the very straightforward way for everybody to use and to get benefit. Now, I believe everybody knows that this is the era of two things. One is new energy or renewable energy. Another one is Industry 4.0, which is digital. And we have been extracting energy from the ground, below the ground, all this while. The gas, the coal, the oil, and that was for the past 100 years. But today, we are extracting energy from above the ground, which is what the next 100 years, or I would say maybe the next millennium, will do. And to extract energy from above ground, there are a lot of challenges because there is a lot of uncertainty that we need to deal with. From below ground, you just extract, you burn the oil, the gas, the coal, you get energy. But if you extract energy from the above ground, which is renewable, then you need to face with a lot of uncertainties that is from the God, which the God will need to give you wind, rainfall, and sunshine, right? So let us start with the case that you might be very familiar because in Sarawak, you have a lot of hydro resources. And Sarawak, but I think today you have around close to 3,000 megawatts of hydro. And one of your big one is Bakun, 2,400 megawatt. Huge. And what is the very important thing for hydro? I put a logo here, is nothing but rainfall. If you don't get enough water, your hydro dam reservoir don't have enough reserve to spin the turbine, you don't get electricity. So weather forecast for the rainfall is very important. Yeah? Now, the industry has moved ahead, and today you will see many industrial players. For example, like EGAT Thailand, the Sarawak Energy equivalent, is already piloting floating solar with hydro. How they try to do this is to synergize between the solar panels power and the hydroelectric power. So you can actually use both of these to meet the grid demand. And this kind of solutions actually, again, is very much depending on the weather. You need to know exactly how much sunshine you are going to get. Is it a rainy days or is it a cloudy days? Or how much water rainfall you're going to get, right? And you synergize both together using machine learning algorithm to optimize the entire performance. So this is where Southeast Asia now, I think including Sarawak Energy, there is a plan for floating solar and hydro as well. So this is the industry trend. And I know that today we are speaking to a lot of engineering students and engineers. This is something that we need to bring to your attention, where the last speaker also talks about the importance of weather, right? And today, what Envision does is we have a team of PhDs who is weather experts, and working with our data scientists, we take the global weather models from various sources like the weather channel, ECMWF, ENCON, so on and so forth. Try to assimilate all this model into a system, running it through a 30,000 cores of a supercomputer. And then we can downscale it to the timing and the resolution that you want. For example, 1 by 1 kilometer in the next 7 hours or the next 2 days, so that you get very accurate weather forecast to that region only. And then using weather forecast coupled with your hydro or your solar or your wind asset, then we run another 3 layers of machine learning like SVM, boosting gradients, and linear regression to come up with what we call the power forecast. Because what we want to get is the power forecast, right? How much electricity you can get from solar, wind, and hydro. So weather forecast is a great input for power forecast, and it is really, really needed. So if in Sarawak University, UNIMAS, there are PhDs or there are master degree students who is into this area, feel free to talk to me because we are recruiting. Yeah. Now, if you want to learn about how we use AI and machine learning to do weather forecasts to help Sarawak Energy even, these solutions is already pretty much deployed with Sarawak Energy. So you can always visit Sarawak Energy, talk to maybe Christopher or any Sarawak Energy leaders. Then they can show you how this AI-enabled weather forecast is being done now. Well, I started with hydro because this is what Sarawak is really depending on. If your hydro dam is not functioning, then you have a lot of blackouts. Now, let me switch gear a little bit to really on digital AIoT. And today, I believe many of the young people or even like the adults have a digital watch like this. And with this digital watch, you don't only get time, you get your heartbeat, you get a lot of all your other diagnostics information like your sleeping pattern, so on and so forth. That will help you to optimize your own health, right? And how you manage to optimize is because of all these different data that you get from your digital watch. If you wear a Rolex or a Panerai, analog watch, you get nothing like that. So the key things is to digitalize. If you don't digitalize, you don't get all these benefits. And in Industry 4.0, if you look at the chart, it is very, I would say this is already very popular, that people knows that you want to get from descriptive to prescriptive. Meaning to say that you know what happened, then you know why it happened, and you are going to predict what happened next, and then try to deal with it, right? So just now, the power forecast, the forecaster, is to really help you to predict what's next. How much power you're going to get tomorrow, 3 days later, right? Coupled with machine learning and the weather forecast. So today I'm going to maybe, switch from just this forecaster to the remaining pillars, so that you know that how Industry 4.0 is coming into act now. Well, the first one is definitely on remote monitoring. And when we talk about DER, distributed energy resources, the keyword is distributed. It is scattered around. Even in Sarawak, if you look at the SARES project, like Christopher has presented, it is actually to power up all the different villages where all our native people, like the Iban, the Dayaks, is living. Sometimes just one long house in one very remote jungle. And then you have systems like solar, genset, battery. So all this has to be monitored so that whenever there is a fault, Sarawak Energy can deploy the O&M personnel to go and fix it. So this remote monitoring is very important. And today, because of all this distributed energy resources demand, there is a lot of need for remote monitoring. And thanks to the cloud technologies, all this is very possible now with a lot of mobile app and so on and so forth. And we do this. It's not nothing very fancy, but it's something that DER really needs it, remote and online monitoring. So in Envision, we have helped, this is one extreme example in China. There is a client that has 1,274 sites. And there are big and small rooftop solar, ground solar, some batteries, some SARES-like deployment, microgrid. We help them to monitor. Yeah. Now, that is very, very quick. I'm going to switch gear to Insights, which is what we call analytics and machine learning. This is what you might be interested in, right? Now, for renewable, for DER, let's take solar as an example. It's the same thing. So today, we deploy machine learning and AI to help you to monitor solar asset. So as you can see from the screen itself, on the right side, this is what you design, right? So let's say you design 53 gigawatt hours, but a lot of time life is not perfect. You only get 43. If you never have the machine learning and AI or diagnostics ability, right, you do not know why this plant is not performing up to the mark that you design, right? So in between here is all the losses. So through a machine learning, you will understand what are the different losses that it contributes to this, like soiling, like shading, like the panel degradation, your inverter malfunction, so on and so forth. So what machine learning is helping you is it quickly learn about your site, tabulates to you what are the root cause, okay, and tell you what are the achievable or recoverable productions, and then put it down here like this for you to see that, hey, you should do this, which is the green one. It will even recommend you like, hey, this is the low-hanging fruit. Please do this first. And if you do this, the return on investment, the payback is fast. So rather than you decide what to do, there's a list of problems. The machine learning AI will pinpoint to you that, hey, these are the few ones that you should do. For example, if you have a tracker, sometimes the tracker of the solar, right, it tracks the sun. Sometimes the tracker is bad. It doesn't even move. So this is what the machine learning will tell you, right? Do this, and then your return on investment is 4.7 weeks, right? Now, not only that, the solar analytics will also tell you like when to wash the solar panel. Sometimes your solar panel is dirty, right? And then how many times you should wash in a year, when to wash it, because washing is a cost. And if you wash every day, yes, your solar panel is very clean, you get all the sunlight, but your cost is so high, right? So with machine learning, it will tell you like what are the optimum time to wash. For example, like 4 times is optimum. And then why? Based on the weather forecast, I know that it is going to rain tomorrow, 3 days later, 1 week later. So I would not wash when the sky is washing for you, okay? And then we'll analyze like how is the dirt accumulating, and then where are the good timing to wash. Okay, so this is again another great way AI and machine learning is helping you. And not only that, right? I talked about the tracker just now, right? Stow and backtracking is what you can do. And then also, if you work with the material science, like panel is just made out of silicon, then you can actually get the panel degradation curve very easily, so that your solar panel is going to be changed out soon. And then like your inverter, sometimes your inverter just act behind the scene that is not good. A lot of things can be done, can be tracked using machine learning. Yeah. Now, these solutions is not something new and something not proven. In Malaysia, TNB, Sarawak Energy's counterpart in West Malaysia, has deployed this in 2 plants, one in the 50 50 megawatt Sepang asset, one is 30 megawatts Bukit Selambao asset. So this is a press release, and you can actually go and read it, online. Just search TNB Envision, you get it. And for this kind of solar analytics, today globally we have more than 600 gigawatts of solar asset, and we are seeing an uptake of this machine learning in all the different players like TNB in Malaysia, SolarVest in Malaysia, Malakoff in Malaysia, so on and so forth, where they install solar, and global client as well. So 40 gigawatts of asset will have been powered up, over 200 clients with this machine learning analytics for solar. So I believe this is the next trend, and there's a lot of opportunity even in a career for this. Last but not least, I think today the topic is all about DER, right? And then my topic there is this battery there. So smart grid or the microgrid, which the ex-presenter is talking about, is one of the way to go. Like SARES, right? You need a battery there. Why? Because of intermittency. Because tomorrow you have sunlight, the next day you might not have sunlight, right? Because of cloudy days. Tomorrow you have rainfall, the next day or the next week it might be droughts. So for microgrid, battery is very important to get all the data to store and to the energy to store and then to release it when you need it. So for Envision, we are a digital company that's do this microgrid solutions, orchestrating all the generating asset like wind, solar, hydro with battery, with EV charger, so on and so forth, supplying to the grid, to work with the grid, when to charge and discharge, when to arbitrage, when to cut off the grid supply so that you use cheap energy from renewables, when to have net zero export because the grid don't want you to export energy. So we've done this project. This is one in Jiangyin, China that we have did. And then battery itself is today not a dummy battery, right? Even in your mobile phone, you can see some of the diagnostic features of your battery. And when you use it in the utility scale, in the industrial, battery itself is even more important if you have intelligence. Yeah. And we did that. Yeah. Now, I will not go very detailed on things, but just to give you. So in Thailand, PTT, which is Petronas equivalent, largest company in Thailand, they are doing energy transformation and digital transformation. So they pilot a microgrid solutions in one of the university in Thailand called Vistec. And they do floating solar, rooftop solar, EV charger, battery, and have all this net zero initiative, net zero export, net zero import. So something that you can try in UNIMAS because of R&D in nature. Yeah. And then obviously for battery in microgrid, we have more use case as well. In the shipyard, right? Today, the shipyard, you need 60 hertz of power to supply, and your grid is supplying 50 hertz. So what you do is you use genset, diesel, to supply power, and that diesel itself is burning and is releasing CO2. So what we do in Singapore with Keppel, one of the huge company in Singapore, is we use battery power energy storage, ESS, to replace this and to help with powering the ship. At the same time, save the environment, yeah, and replace the diesel. And the return on investment is about 5 years and 45% ROI. This is the last year project when the ESS, the battery, is still expensive. By moving forward, just like solar panel, the ESS, the battery price is going to go down. So the return on investment is even better, yeah, moving forward in the future. Well, I have not introduced Envision Digital. So Envision as a group, we are an RE100 company, meaning to say that we use only renewable energy asset moving forward. We are a wind turbine manufacturer, which is based out of Shanghai as a headquarter. Envision Digital is a Singapore company. We're based out of Singapore. Envision AESC, our battery storage, our battery or ESS company is headquartered in Yokohama, Japan. We have an investment arm in Silicon Valley, and we also really piloted this we acquired the Virgin racing team from Sir Richard Branson, the Virgin Group. So now the electric vehicle racing team, Virgin, based out of London, belongs to Envision. So we are, multinationals. And last but not least, as I mentioned, we are huge in AI and IoT. So our AI platform or IoT platform now is powering up more than 180 gigawatts of energy across the world. Some are wind, some are hydro, and then 60 million devices. And we have all these domains that is available, like smart cities, smart building, smart industrial, smart mobility. Yeah, and we're accredited by the Singapore government. So that's so much from me. And we believe that with digital, with renewable energy, we can orchestrate beautiful life. And if you want to get in touch with me, here is my contact. You can add me in LinkedIn or you can drop me an email. Thank you so much. Back to you, Mr. Host.
Yes, yeah, thank you, Mr. Whitehead, for this interesting presentation. And now we will go for the question Q&A, participant. We have one question for the Dr. Hazrul. Yes, you can hear me, Mr. Whitehead, yeah? Hello? Oh, we have one question,
yep.
Mr. Yeah.
I can still hear.
Yes. So Dr. Hazrul said, may I know how long is the protective horizon your solution can offer for solar radiation?
How long?
Yes, how long it will be the protect for the horizon for your solution can offer for solar radiation?
Solar radiation. I don't get the question, but for power forecast itself, let's say we can today we are complying to GSO, which is the TNB grid operator in West Malaysia. So they have some different mandatory, like they want a day ahead forecast, 3 day ahead forecast, 7 a day ahead forecast. Depending on the grid. In China, they want 7 hours ahead forecast. So it depends. We can customize based on the requirement.
Okay, thank you so much. So, any questions from the audience? You can drop the question A box, or you can unmute you if you want to ask for the Mr. One. Just raise the hand, and we assist you to unmute your mic, or you can drop your question in the Q&A box. Yes, audience, any questions? Any extra questions? You can drop your question in the Q&A box, or you can unmute your microphone directly, Mr. Wantian, yeah? Yes, I think no more questions, Mr. Wantian, and we want to thank you so much for your presentation and for having you for this section. Thank you so much. And now we invite the next presenter, which will be the Dr. Hazrul. You can hear me, Dr. Hazrul, yeah?
Yeah.
Yeah. Okay. So Dr. Hazrul Muhammad Basri, he's a lecturer in the University Malaysia Sarawak, Department of Electronic Engineering. He's specialized in the renewable energy, and currently he's work on the solar energy technology and development. So Dr. Hazrul, if you are ready, you can share your slide. Yeah.
Okay. Okay, Bismillahirrahmanirrahim. Welcome everyone to my presentation. So just a bit of myself. I'm Hazrul bin Basri from University Malaysia Sarawak, and currently I'm a senior lecturer in the Faculty of Engineering. So actually today I would like to just share my experience on a case study to be more specific on solar PV design. So the title of my presentation today will be Determination of Optimized Standalone Solar PV Design Using Technique of Order Preference Similarity to the Ideal Solution, or TOPSIS. So actually, when we talk about optimal design, we normally relate with MCDM, which is the multi-criteria decision making, and it is also related to the level of intelligence, your wisdom, and creativity in solving the problem. So the technique of order preference by similarity to the ideal solution, or TOPSIS, actually is one of the well-known distance-based approach for decision making. So what it does, actually, it ranks the alternative with respect to their geometric distances from the positive and negative ideal solution. So in brief, actually, TOPSIS is based on aggregating a function of the evaluation score and determine the best alternative by some mathematical equation. So you can see later on that actually this technique, even though it gives the best solution, but the step you take to find out what is the best solution is not that difficult. So this is the advantage of using this TOPSIS method. So instead of TOPSIS, we have different techniques like the Promethe, AHP, the ADAS, the entropy technique, and so much more. So here I'm just sharing my experience in the form of case study, a real case study, using the simplest technique, which is the TOPSIS. So actually, when we make a decision, there will be a lot of trade-off among the objectives. So you need to evaluate the pros and cons of each alternative based on multiple criteria. So the objective is to find good compromise solution that perform the best, satisfying all the objectives simultaneously. And actually, this technique will give you a rational, justifiable, and explainable decision. Of course, as a human being, you can base on your feeling to make decision. But in engineering decision, you need to the decision must be supported by scientific reasonings and mathematical calculation. So here I'm going to share some of my case study. So basically, when we design this solar PV installation, I will be based on the SEBDA guidelines. SEBDA stands for the Sustainable Energy Development Authorities, which is the highest authority in Malaysia to decide on the renewable energy action. So all this calculation is based on the guideline, and these are some of the equations that I use to design the battery. So here, from this battery, you can get the number of series, number of parallel, daily depth of discharge, and so on. Okay, and also when you design the solar PV system, you need to base on the local standard. Like for Malaysia, we use the MS1837 or MS61275, for example, and these are the standards on how to design a good and optimal solar PV design. But the problem is, normally the design will give you in terms of range. So what will be the minimum and what will be the maximum? So there is no ultimate ultimate solution. Which one of these within this range will give you the best solution? There's nothing such as that. So TOPSIS will offer you a very simple solution which can tell you, based on scientific reasoning, what will be the best and optimal design. So again, I refer to the Malaysian standard and the guidelines from SEBDA. So these are the equations given by the standard. So I just simply follow this equation, and we get the absolute maximum voltage and the highest voltage of maximum power. This is just to maintain that, to ensure that the MPPT is working within the range. And of course, this is important because normally for solar PV installation, we have a lot of components like, for example, battery, the solar charge controller, the inverter, and those components need to interact with each other. Okay. You cannot simply connect, for example, 20 kilowatt solar panel with 5 kilowatt charge controller, there will be a power mismatch. In order for this component to interact with each other, the power rating of each component must mutually match. So the purpose of SEDA giving these guidelines is to make sure that the power rating of each component match each other. These are the some of the calculation. Actually, there are a lot more calculation, but I just share with you the most relevant one. Okay, sorry. And from this, you see, here I try to determine the maximum and the minimum number of solar module you can connect in series. Same thing goes for the maximum number of solar string you can put in parallel. So this thing is, if you look at this equation, it gives you the solution in terms of range. It gives you the minimum and it gives you the maximum. Same for the number of parallel, number of string in parallel. There is no such thing as, okay, you perform the calculation and automatically you get the optimal design. This is just in terms of design. So when you talk about the solar PV installation, you need to consider the cost, losses, the design, number of components, and many more. I will go into detail later on. Okay, this is another calculation for the selection of blocking diode, bypass diode, capacitizing, and so on. Okay, for this case study, what I intend to do is that when I talk to my to one of these client, he agreed to use solar panel which has rating of 430 watt peak and 450 watt peak. And then for the selection of inverter, we have two solutions. Based on the price criteria and reliability criteria, we have two options. Either we go for the hybrid VTX 30 kilowatt, this one is from ProLink, or we go for the 15 kilowatt hybrid inverter from Voltacon. So here you need to play around with four components. Okay, 430 watt peak panel, 450 watt peak panel, ProLink inverter, and Voltacon inverter. So now we can goes up to 4 design. If you make the combination, you can go for up to 4 designs. And this is the load profile that I've taken from the client. So this is actually a 3-phase system where you have the phase 1, phase 2, and phase 3, phase R, Y, and B. So I list out all the components and the power rating, the power factor usage, and so on. And from this load profile table, you can come up with a total maximum demand that you need to design. And of course, you need to consider the solar irradiation and so on. And based on the calculation we have made earlier, okay, the equation before this, we have come up with this one. So first, I consider design number 1. For design number 1, I consider solar panel from Longin, 430 watt peak, and Voltacon 15 kilowatt hybrid MPPT inverter. So when I apply the formula that I've shown earlier, so these are the solution. And the best thing about TopSys is that because the algorithm is quite easy, you can pre-program using Excel. Okay, once you do that, the Excel will automatically give you this solution based on the formula you have input to the cell. So we have 59 solar panel we need. So this is the minimum. Again, the solution is in the form of range. Maximum parallel MPPT 1, and then for minimum series is 11 and maximum series is 17. So meaning to say that actually you have several alternatives, and we need to find out which one of these alternatives will give you the most profitable design. Okay, and of course you can come up with the number of MPPT, and of course price is one of the criteria. So we need to list down the price of each component, the shipping price, and so on. And we have alternative number 1, this much of ringgit Malaysia we need to spend. For alternative number 2, this much of ringgit Malaysia we need to spend, and we perform this calculation for the rest of 7 alternatives. So upon discussion with the client have decided that you need to consider 4 design criteria. First is the price, second is power generated, third is the number of solar panel, percentage of power losses in the DC cable. So I just key in the value from the datasheet, and these are the numbers that I come across. Okay, for alternative number 1, the minimum is 11, and then it goes to up to 17. So in total we have 7 alternatives. And then for second possible design is I use, instead of 430 watt peak, I use 450 watt peak, and I combine with 15 kilowatt hybrid activity inverter. So these are the numbers that pop out from the Excel. And here again we have 7 alternatives. So from the design number 1 we have 7. So now for second design we start with alternative 8, 9, 10, 11, 12 until 14. So I list out all the possibilities. If I use 11 in the string, 12 in the string, 13 in the string, I list out the price you need to spend for this kind of installation, the power generated, number of solar panel, and so on. And then the third design, I just change the solar panel to long again for 30 watt. But this time I use VTX 30 polling hybrid inverter. So it's quite repetitive, and now we get this solution. Here, the minimum series is 15 and maximum series is 18. So meaning that we have only 4 possibilities. So design number 1, 7 possibilities, design number 2, 7 possibilities, and design number 3, 4 possibilities. So it starts with 15, 16, 17, and 18. And I do for the last design. I do it for the last design, and I get alternative 19 until 2022. And this is where the top 6 start. So we need to consider all the alternative from design number 1, design number 2, design number 3, and design number 4. We need to concatenate all this alternative, and we list down all the prices, power generated, number of solar panel, and percentage of lost in DC cable, And then we need to perform this rooted square sum of square of each performance score. This is what you call as performance score. Okay, this is the performance score. We perform this calculation and we get some values here. We do it for the rest of all attributes. Okay, attribute price, attribute power generated, number of solar panel, and so on. And the second step is to normalize the performance score. The way you normalize the performance score is you take the numbers inside the cell and you divide by the rooted sum of square, and you get these numbers. And now all these numbers are normalized. And the third one, you need to multiply the normalized performance score with the weighting factor or weightage. So this weightage actually explain how much percentage of the design, how much of the attribute contribute to the design of your installation. Let's say, for example, upon discussion with the client, he said power is the most important. So we can put a weightage of 0.5, meaning that 50% of the design must come from the power generator, and then 30% from the price, 10% from the number of panel, and 10% from the losses. So here there are 2 categories: cost category and benefit category. For the cost category, we need to assign VJ plus, which is the best ideal solution, and the best ideal solution must be the minimum of this number of all these alternatives. Because if we reduce the cost, meaning that the design is better. I mean, it is more desired. While the less ideal solution will be VJ minus, which is the max. Of course, when we talk about price, if we can lower down the price, meaning that the design will be a better solution. Meanwhile, for benefit, it's the other way around. We have VJ plus. We take the maximum out of all this normalized performance score, and we take the minimum for the less ideal solution. So we can simply perform this calculation and you get these numbers here. And last but not least, we need to find the what we call as the relative closeness. The relative closeness, first you need to find what you call as Si plus. So Si plus actually represent the Euclidean distance from the ideal solution. Si plus, okay, I repeat, Si plus is the Euclidean distance from the ideal best solution, and Si minus is the Euclidean distance from the worst ideal solution. So we simply perform this calculation, we get the Si plus for each alternative, and Si minus, which is the Euclidean distance from the worst ideal solution for each alternative as well. So we tabulate all these numbers and we perform this Pi equal to Si minus over Si minus plus Si plus, which actually give an indication of how close is the solution to the best solution. So based on this Pi, the performance index, you can rank these numbers, which the highest will be rank number 1 and the lowest will be rank number last. And based on this simple calculation, we have come up with a decision that alternative 18 will be the best design. And alternative 18 come from the design number 3. Okay, let me just bring you back to the slide. Alternative 18, we need to use 18 series in 18 solar panel in series, and it will give the best trade-off. How to say? Okay, the best trade-off choices for the client, both client and the designer. Okay, I guess that's it for my presentation.
Okay, thank you so much, Dr. Hazro, for your presentation. So, as usual, we ask the audience if anyone have questions to ask for the Dr. Hazro. He can raise his hand to unmute his microphone, or he can drop his question in the Q&A box. So please, if you have a question, please just update that. You can type your questions and we Dr. Hazro, or you can raise your hand to mute your phone. Open to the floor. Any questions? Yes. Okay. So I think it's no question from the audience. So if you have a question later in the end of that's all presentation, you can drop your questions and we can give it for the panelist or give it for the keynote speaker later if you want. So now we move for the second presenter. Okay, so yes, Prof. Musa, you can hear me?
Yeah, I can hear you, yes.
Okay, so now next presenter is Dr. Musa Muhammad Ahmed. He's currently with the Department of the Electronic Engineering, Faculty of Engineering in University since July 2016. Prof. Musa is as a IEEE senior member and has been for IEEE for the past 22 years. The specialization and research for the Prof. Musa to be include sustainable renewable energy, smart grid technology, and digital substation development. So, Prof. Musa, if you can share your slides.
Okay. This is my screen, right?
Yes, you can share your slide. Yes. Okay. Yeah, you're already sharing the slide now. Just the button, yeah.
You see it?
Yes, you can see it.
Okay. So I have two slides. This is one, and I will go to next after I finish this one.
Okay.
Okay. My title is Digital Technology Applications in Energy Industry. I will go for a generic explanation what happens to the system, and then I will give some standard of how to develop technologies on the industry, and where are we now, and we have to start from here. And that is what I'm going to explain. So digital technology applications to energy district, Malaysia case. Okay. So let us see the I cannot move the things. Huh? Cannot move the. Have to use the. Okay. So what we can say, the executive summary here: power system demonstrates shifting from traditional rigid system to multidisciplinary paradigm that has yet to materialize in its full swing or moving greater territory of applications and mixed technology. We know our system has been rigid. Our generators, our transmission lines, our transformers, all our major electrical power systems were rigid. They were not connected to what do you call it, modern communication systems or IEDs or modern remote control systems from the beginning. But this actually traditional power, which has been rigid for a while, is changing now to a multi-paradigm technology, whereby we can use multidisciplinary technologies to improve the system. So there are issues here. So what we actually talk about here is application of smart grid and digital technology, which has been motivating force for the shift of this paradigm shift. The purpose of this paradigm shift necessitates prioritizing the three pillars of power system: generation, transmission, and distribution. So generation need is balance between solid grid and islanding with microgrid and renewable energy integration. Transmission lines to avoid fault cascading system that creates blackouts and look for self-healing system to operate. Outage, low efficiency because of losses, false trimming by relays, lack of detecting the faults, transmission line trimming, which creates cascading of the transmission line system, and that creates also what you call it, the outage or blackouts. So these are the issues. Distribution system should be automated and deal with demand side management and also what you call demand side response. So digitizing new substations, refarming their electrical components is a necessity for near future technology additions. So what we are talking about, like additive technology or additional technologies to be used in order to reduce the losses, increase the efficiency, and also eliminate outages. Okay? So the technology we use normally, we call it smart grid and digital technology. Okay? So to name few, we have enabling technologies based on smart grid system, right? That increase the safety of electrical power system and also increase controllability and interoperability, right? And we have those technologies. We are two-way communication systems, protocols, intelligent electronic devices, emerging units for substations, big data analytics, cybersecurity, communication technology, ICT, and Internet of Things. Also, deep learning, artificial intelligence. All these are techniques nowadays are very popular to use the power system. So from here, you can see my what we call the content is here. So we have expansion plan strategy, we have Gantt chart, we have talented development, we develop those technologies. We have technology which involves change with the time, technology development timelines, we have technology development stages, we have industry transition, including the utilities, because our utilities are in transitional because of the technology which is changing. Digital technology components, digital technology is starting, right? It started, and also you operate it and then you get the output. A data analysis or data usage, R&D driven technology, digital technology stakes, sustainability of digital technology, So we have all those components here. So if you look this Gantt chart, we have everything here from foundation to test tools to branding. So that is the technology, how the technology evolves from the beginning to the end. And if we start in 2021, what are you expecting, you guys in the industry, the utilities? Okay, we have a problem, money problems in the utilities. Those who are operating, they have problems. So you have whatever I mentioned just now. But for example, if you take an example, you have a relay which have been used for a while, and also technology is changing for those relays. But if you now look at the technology now, what do you have? You have a relay which cannot see the fault sometimes, which actually creates fault tripping. So these are the issues. So if you have thousands of relays connected to your system, and what do you say? You say, okay, I wish I will get a relay, smart relay, which can detect the faults, exactly the location it occurs, and also tells me which type of faults. Of course, the indicators are there at the moment, and also the relays which cannot show the fault reading or cannot treat the fault where there's no fault. So that word which I wish is a click whereby you can actually, you have the answer. Whether you want it to react or not is up to you. But this technology, you cannot wait till, okay, you can say, okay, I am using the same relays and I have same problem, and you are expecting that the life will go on. So it's not actually an option. So you have to move. How you want to move? You have to follow the technology, go with the technology, start somewhere, and also involved with the technology. So, but nobody will give you a relay, right? A salaries, but you have to try your best to design your own relay one day. Maybe 5 years from now, maybe 10 years from now, and it depends. But you have to react now because you have a problem and this problem is coming up on and on. So these are the stage contact. This contact shows you how you can start, but you have to be serious and also you have to aim to solve this problem. Okay, and one of the issues is the talent development. Of course, we have men and women working with the system. So talent development is very important. Tools are very important. And also research is very important. Research and development is very important. And product is the next stage. If you do this, train your talented people and also give them the resources and also do the research. At the end of the day, you can solve this problem. So you will never repeat this word, I wish I can get a relay which can not trip when there is no fault. Okay? So that is what, and actually my talk on this side is motivation. So I want to motivate the utility so that they shouldn't close their eyes and wait when the time will come. We are in the stage of the pandemics. Okay, we don't know if the technology pandemics will come. Who knows? Last year we were not expecting pandemics will come, but now we can see our situation. Our ENCON is online. Okay, our classes are online. So this situation of technology pandemics can occur, guys. Can occur, yes, can occur. There are so many companies who get out from the market, no more. And they were the largest companies in the world. Why? They didn't see the future. So the time was up. They could not do anything. Others took over. Nokia was one of them, right? And the giant energy company, right, was there. And they are no more here in this world nowadays. Okay, so this is the technology, development technology. She said time. This is how you want to go when you want to develop your technology, whether you are in the industry or wherever you are. This is how the technology will move from the beginning to the end. And the concept presentation, concept verification, and also prototype verification will come. And finally, you commercialize your relays. The relays, my example today is a relay, right? And guys in the SEB, I'm talking about differential relays. That is the best relays you have now. Okay, so that relay will never sustain, right, your systems. Okay, so this is the stage, technology development stage, activities, right? So you start with identification of the project, right? And you have targets, right? And finally, you get your prototype and you produce your product and you deploy it where you want it to deploy. Okay, so this is industry transition. Okay, this is the technology transition. If you look at the traditional system from bottom there, one, then we go to SCADA systems, for PLCs, we go automation systems. Now we are SCADA, what do you call it, smart grid and digital technologies. And finally, where we are going to, next 5 to 10 years, 5G, IoT, IR, 5G. So this is the technology, the digital technology components. If you use these components of digital technology components, then you can have a complete digital system which can solve your problem. So these are, we started now, the technology and how we go. Let us involved with it. We have technology output, okay? And what we have, we got all those. These hours, okay? And we have data analysis usage. That's one part of it, okay? You have to be on the map so that utility, the people say that utility is the best. So you are on the map now. You cannot escape anything. Everything's on the map. We have digital technology age. Research and development driven methodology is there. So you can see the focus is to 2021. If you start from there, that is how you go. Okay? That is in percentage wise, what can you achieve, right? Each year. You can see you reach 90% by 5 years' time. Okay? So this is the integrity, sustainability of digital technology. You must have this if you want to implement it. Any organization must have integrity, leadership, resourceful, talent development, and productivity. These are the issues. Okay, importance of the usage of social media is there. Energy transformation now started. So we have our in UNIMAS, we have one energy transformation project. So we are designing a system based on GIS, special technology, so that we can find out how much renewable energy in kilowatt you can get, you can find any kilometer of Sarawak, any kilometer. Any kilometer of Sarawak, you can estimate how much power you can generate. And this power could be hydro, could be solar, could be wind. These are the digitizing energy sources. So you can use GIS, GPS, digital technology, mapping, quantifications, and all this by using digital systems. Which is simple. Malaysia digital economy started and it's going on. And now the people commercializing this technology. By the way, we are digitized already. You guys, we are already digitized because we are using iPhones and iPhones. Okay, so this is the digital economy in Sarawak state. Okay, you can see Sarawak is already digitized, right? Technology development in Sarawak, you can have this. There are these digital stages. You can see there, create, focus, develop, produce, patenting, and commercialize. Okay? This is the technology, population-driven technology. You cannot ignore the population, right? That 100% of the population will be the, what you call it, digital technology driven. Final stage, and you get your product. Thank you very much. Do I have a time?
Yes, for Musa. Hello.
Do I have a time?
I think we have a short time, Dr. Musa. So, do you have another slide or this one?
Okay, so I end up.
Yeah, because you have now the lunch hour, it will be 1 hour, and we return start at the 2 p.m.
Okay, thank you very much.
Yeah,
Thanks a
thank
lot.
you, thank you. So open the for the audience, open the question Q&A
Any
section.
questions, guys? I'm ready for question and answer.
As usual, if you have some question, you can type it in the Q&A box, or you can request for the mute your microphone to ask Prof. Musa directly. If you have any question for the audience. Yes.
SCP are not there?
And also we need after Prof. Musa, we need to open the Q&A section for the all presenter, for all the brief presenter. So if you have any question, you can drop in the Q&A box, or you can request for the mute your microphone. Okay, for audience, any questions? Yeah, Mr. Ho. Hello.
Hello.
Hello, yes?
Yes. Yeah, you can ask. Yeah.
Yes, Hao Tian.
Hello.
Hello,
Nice to meet you.
welcome. I hope you are from SAB.
Myself? No, I never worked for SIP before.
Okay, most welcome.
Thank you.
So any questions?
Yeah. So any question for the all the presenter for the keynotes? We have all the keynotes here. So if you have any question, you can just drop in the Q&A box, or you can mute your microphone.
Oh, I can't. Maybe I cannot hear. Is it?
No, I think still not anyone ask question, Dr. Prof. So we can give a chance before we end up this section, because we 2 o'clock, 1 o'clock we start lunch time and break time to the end.
Thank you very much.
Thank you so much, Prof.
Thanks, Jonas.
Yeah.
Thank you, Jonas. Thanks, Siawan. Good
So
guys.
I think no more questions. So I think we have to end up this section, and we will continue after 1 hour. We'll be started at 2 p.m. by Asia time. So I hope I can see you later if you want to join for the next section. Thank you for the presenter, and thank you for the all audience. We see you later at 2 p.m. Thank
Okay.
you.
Thank you. Bye-bye.
Thank you. Thank you, everyone. Bye.
Thank you. can share. Can share. Yeah. You can see. Welcome. Okay, welcome. There's sound. There's sound, bro. Oh, yeah. Okay, bro. Hmm? That's still not bad. Everything to think.
First screen, you play the video, people can hear the sound. You need to share the video. No. You need to stop sharing the video.
Yes,
No, stop sharing screen.
because they can see it.
Yeah, can yeah.
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 Mr. Hazrul, you can hear?
Okay. That's it. Yeah. Whatever you do.
Yeah.
Okay, look from my
Yeah, you can. They ask.
Okay, whatever.
Hazrul, did you get the lunch? I have lunch books there. Yeah.
Video are you? Video.
I am fighting with certain point, and people are writing this very nice.
What is that?
Yeah, dia comment. Got so much noise. People talking behind. Dia tak tahu. Yeah. Eh. So you're still only the
Yeah, already take it. Yeah.
Enjoy yourself.
Okay. Wait. Already
Just let
shared.
it run.
Yes.
Recording. Not add. Not add. No, I mean,
Pack lunch.
Yeah.
Oh,
there.
okay.
The computer, yeah. Yeah, the computer, I think.
Pack lunch. So, what did I do? Apa lu tu aku
Oh. Just now, yeah.
Yeah, I was sleeping the whole hour, the last towards the end. I was like,
For me, kind of difficult, you know. You know how you can do it, yeah.
I was very curious of share. Yes.
It's very difficult. For me, I don't like that code, you know. If you do, I cannot do nothing.
Yeah, but you can't go because you're on the camera.
Yeah.
You can't go.
You cannot do it. You have to be sacrificed, yeah. Yes, I want you to the sound. Yes. Yes, yes. You can. Sure. Okay, okay.
Okay.
Now I'm the host.
Yeah, you are the host now.
So meaning that now I can appoint.
Yeah,
yeah, yeah.
very good. Thank you. Thank you. No, okay. Okay, so now we keep it like this. Yeah, you are the.
Yeah, I think I can just log up.
Okay. Buenas, mira. Yes. Someone said, they said, he said, can this share with my colleague? You already got it? This means he's one. Is it? Yeah, because not okay. Okay.
Asing to record by himself.
Yeah, I think it's better. Yeah. Easier thing for him. So this is okay done. So this is but which one will start with? One of these three will start.
This one is the this one is the conductor, but I don't find any biography about him. You can find it, maybe you can put now. What is it? Dr. Azhan. Israel. TNB, I think, TNB, but I don't find something directly. Let's need a few more. Each time paper, maybe. The paper in the paper. So this is clear. These are some of his papers. But 4 or 3 of these people, but not written native. I find many format community, but I don't know the last one, the latest one.
It doesn't even have Google citation.
I can't find. That's the one. Is it? This one is really control systems. There's only one, maybe it's not it all. Can you open any paper? The picture you have it down. Oh yeah, yeah. Into the paper. Current. But current, what is position current?
Well, current position is someone. TNB, yeah?
TDX. Yeah, something TNB.
Retail division.
Hmm?
Retail division, TNB.
4 September.
TNB retail division.
Can you copy?
Sorry?
Can you copy? Yeah. Just put anyway. If you need to introduce it. You would like to introduce it better? Yeah, better.
Yes, yes.
Yes.
Yes. Can you hear me?
Yes.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good evening. So today, now is the second session of our special track, SEB special track. So our first presenter is from the Sarawak Energy Berhad. Will be delivering his speech on the DER system design in Sarawak, combination of mini hydro, biogas, and solar. Can I get the feedback from SCB? Who will be the representative for delivering this topic? Anyone from S? Yeah. Okay, Mr. Chan Wen Xiang. Okay, you will be the one presenting. Okay. Now you are the panelist. You can share your screen and you can start presenting your topic.
Hello, testing.
Yeah.
Okay, let me share my screen. The share button is gray.
I can present.
Can you please try now?
Can you try?
Yeah.
Yeah, now okay already.
It's okay. Yeah. Okay.
I'm not sure. Can you see my video?
Yeah. Yeah. Sure. Just a simple reminder, every presenter will have 15 minutes of presentation. You may present in 10 minutes and 5-minute Q&A, or you can adjust your time in such a way that we have 15 minutes per presenter.
Okay, all right. Yeah, I get familiar with the system. So can I start now?
Yeah, sure.
All right. Good afternoon, ladies and gentlemen. First of all, I would like to express my thanks to UNIMAS and the event organizer for giving me the opportunity to share my experience. So my name is Chan. I'm working at Alternative Energy R&D Department of Sarawak Energy. In this presentation, I will share about the distributed energy resource, which mainly focus at solar and mini hydro. Okay. So, conventionally, most of the utility company are using large source of power plant to supply huge number of residential, commercial, and industrial customer. In Sarawak Energy, we have a lot of mega power station, including Bakun, Batang Ayer, and Mulun. So those installed capacity can goes up to few thousand megawatt. As comparison, the distributed energy resource are small and modular energy generation, which typically come from renewable energy. The example is photovoltaic, microhydro, wind turbine, or biomass. Other than this, the small genset and energy storage system also considered as DER. Because of the small capacity, the distributed generation can be installed near to the consumer side. For example, you can install the solar on your rooftop. So the benefit of DER is that the capital investment is very low compared to the mega power station, and it able to improve the reliability of power supply. Because this energy is installed near to the consumer side, the energy losses are greatly reduced. Imagine if you have to use the energy which generate from far away, the electricity had to go through the step-up transformer, a long transmission line, and then step down again to reach your house. So there a lot of energy have been wasted during the transmission process. So in Sarawak Energy, the small renewable energy is mainly consists of solar and micro hydro. As you can see from the statistic here, in 2019, the total installed capacity is 26 megawatt. We expect this number to increase to 59 megawatt in 2020 and 62.5 megawatt in 2021. However, due to the COVID-19 outbreak, we believe some of the project is delayed and maybe they have to complete in next year. So this diagram shows the overall design of the solar system. For the first step, we need to know where is the location of the solar, and then to gather the weather data and the load information. From the product data sheet, you need to select what kind of solar panel, type of battery and inverter to be installed. For example, in solar, commonly there are three types of PV module, which are monocrystalline, polycrystalline, and thin film. So, and if you look into the market, there are over thousands of manufacturers available. So you need to conduct a proper cost-benefit analysis to decide the overall system configuration. Depend on the size of the solar system, and if you are connecting them to the grid, you need to comply to the regulation from utility company. After installation, you also need to consider the operation maintenance, and is there any monitoring function, and who is going to manage the asset. So all these are the basic requirement that you need to consider when designing the solar. So I go through the load estimation. First, you need to list out all the electrical apparatus that you're going to use. For example, in the diagram, show this. So in here, this is the typical appliance for the household in Sales. Normally, this appliance has the power rating that measure in kilowatt. Example, you are buying some bulb from the market. You always can read the kilowatt rating. So the typical rating for the bulb is around 9 watt or 12 watt. So it depends. And then if we sum up all the power rating for every appliance, we are able to get 1 kilowatt per house in this example. So in another meanings, if we turn on all these appliances together, then the total power will be 1 kilowatt. So we need to know this number to size the inverter to make sure that the inverter able to gather the peak load and it will not trip when you turn on everything. Yeah, in terms of energy, we will measure it in kilowatt hour. Basically, you need to know how long every of these appliances going to be used. So we multiply it with the number of hours to get the energy consumption. In this example, we get the energy per day is 3 kilowatt hour. And then we're going to use this number to size the PV and the battery capacity. For energy storage system, there are two common type of battery that widely used in solar system. There are lead acid and lithium ion. Both of them have pro and con themselves. For instance, lead acid, the price is cheaper. However, they only can discharge out to 65%. And then the design life is which is 5 years. In comparison, lithium ion is more expensive, but you can discharge it up to 85%, and the design life is longer, which is 15 years. Depend on the project. Sometimes we are prefer to use lead acid because of the lower capital investment. If the project is more to long-term investment, we will recommend lithium-ion because of the lower lifetime or lower life cycle cost. Okay. Next, we move on to the PV module sizing. Since solar is the only source of energy, so you need to ensure the PV generation able to meet the full day load requirement, plus the overall system efficiency. As we know, the inverter is converting DC to AC, and during the process that charging and discharging of the battery, there will always be energy losses. And over the year, some of the equipment may be degraded. So it's very important to oversize the PV capacity to include all these losses. So in our system design, normally we put the system efficiency around 80%. Again, this number is depend on the brand and manufacturer. So you need to double check at the product data sheet and calculate the exact value. The next thing to consider is the shading effect. So if the solar is installed in the rural area, for example, shown in this photo here, you have plenty of option to find a flat area for the PV installation. However, in the town area, the rooftop, the space we have is very limited. So probably in the morning or evening, some of the PV module is shaded. So you need to measure what is the shadow effect for more accurate PV sizing. So we are using the solar pathfinder shown in the first photo here. Is a tool used to measure the percentage of shadow over the whole year. So ideally, we want to find a location that less shadow as possible. And for the irradiation, solar irradiation profile, even though Malaysia is located in the equator, but the irradiation profile is not flat over the whole area. So I will show this is the map extract from the solar GIS website. So you can see that the irradiation is less in the Kuching area up to the central region. For the northern region, they have higher solar irradiation, which means if we put the same solar panel in these two locations, then the amount of energy produced will be higher at the northern area. So this map also explains why sometimes you feel the weather is hotter in some area. Okay. So just we go through the solar and battery component, which is the main component of solar system. Other components include the inverter, charge controller, and the cable. Cable, there are many cable like solar cable, battery cable, and so on. So all this we need to check individually. The design is very much depend the PV and the battery configuration. For example, you see from the photo here, we have 4 PV module connecting in series. So we call it string. And then total we have 3 string. And then all sum out together, we have 12 number of PV module. So let's say we have a more number of PV connecting in one string. So the voltage of the string will be higher. So you need to use bigger cable or different size of inverter. So overall, the system design is very subjective. It depends on what kind of product you're going to use. For each project site, you need to go through the design process and come up with the sizing that follow the site requirement. So just now we talked about the solar design. If money is not an issue, basically we can install the PV at any location as long the sunlight is available. However, for mini hydro, the case is different. We need to find a good river and sufficient elevation to produce the gravitational potential energy. So these are some photo of the mini hydro that operation under Sarawak Energy. You can see that the intake is constructed on the river bank. So the design also had to consider the fresh flood issue. Therefore, the hydrological study is very important. So the design is always started from the desktop study. So we had to look into the rainfall data, the water catchment area, and also from the topology map, we can estimate what is the elevation profile. From this data, we will identify the potential power and find the location of the site. In terms of the design flow, we need to ensure is the water flow is available at least 70% of time in the year. So even though it's 70%, which means there are still 30% of the time that the water is not sufficient. So in some critical location, we maybe set the requirement up to 90 or 95%. Or alternatively, you can add diesel generator as a backup generation because mini hydro is purely dependent on the water. So sometimes in the dry season, maybe it can last for a month. So you need the backup generator to back up the power supply. Okay. After the desktop study, we need to go to site and verify the data. The information we get from the desktop study is mostly come from topology map and the satellite data, which is the accuracy is very low. For example, the elevation profile that we measure from the map maybe is 50 meter. However, when we go to the site and measure, the actual one is maybe is 20 meter. So this is a huge difference. Sometimes all these mini hydro, the head is around less than 100. So any decrease of 10 meter, you will affect the power potential reduced by 10%. So for the water flow measurement, the result also very subjective to the weather. For better accuracy, measurement has to take few times. We prefer one in the monsoon season and another time at the dry season. So by doing this, you're able to know what is the maximum and minimum river flow and come up with a more accurate design flow. During the site visit, it's also very important. You have to interview the villagers because they know this area is flooding or not. Also, you have to ask the village what is the activity that happen in the upstream of the river. So all this information only the village know the answer. So you cannot get this from the desktop study. So after we know what is the water discharge and the elevation profile, we can select the turbine based on this chart. So in the micro hydro industry, commonly we are using Pelton, Francis, Kaplan, or cross-flow turbine. So for example, in the mountain area, normally we can get a very high elevation, but the river is very small, which we will go in the type of turbine that's suitable for this location will be the Pelton, shown in the blue color here. So in general, the design of micro hydro is very focused more on the hydrological study. So it's very important to make sure the water is sufficient to run the turbine in most of the time. So moving on, I will talk about the different type of distributed energy connection scheme. So we have on-grid and off-grid system. For the off-grid, normally this system is to supply to the remote area. The main objective is to provide electricity to those areas that that the grid is not available. And because of the high capital cost, the energy usage will be really limited. In the comparison for on-grid, the main intention is more to reduce the electricity bill, or some of them, they want to install the solar because of the green building requirement. So in either on-grid or off-grid system, you need to follow the system voltage and frequency shown in this table. For instance, the voltage you have to set the operating voltage along +5 to -10%. Then for the frequency will be 50 Hertz ±1%. So this is really important to ensure that the appliance that you connect will be not, you don't want to damage your equipment when you home back the supply. So there are, in terms of generation control, there are 3 types of control mode. The first one will be the island, which means there are only one single generation. So in this case, the generation output will follow exactly the load demand. The second scenario is the mini grid, where you have more than one generator. For example, you have solar plus diesel generator. So the generation output will be based on the load sharing, or we call it loop control. In this mode, all the generators are working together to share the load. And the last scenario is main grid connection. So this during the main grid, the distributed generation able to run in maximum power. For example, we have a mini hydro, and then we can generate a full power if the water is sufficient. And then we can turn off the mini hydro anytime we want. However, in the island and mini grid, if we turn off the mini hydro, that means it's total breakout already. So we cannot do that. And then even the water is sufficient, we also cannot simply run at full capacity, because if you do that, you will overload the whole grid system. So in terms of the protection, if the DG is connecting to the main grid, we insist the anti-islanding protection must be included. So this photo shows the typical diagram of the distribution network. On the left, we have the main grid, and then we have a breaker along the line, and then the DG is connecting near to the customer side. So if anything happen at the line, if any fault happen at the line, the breaker, it will trip. So you need to trip the DG immediately, because the breaker here is designed in such a way that after a few seconds, it will recross back. So we want to prevent the scenario that it recross onto the island grid. So this is a very safety issue if we connecting two sources without synchronization. So for the designing of DR, there are many more considerations, just like the point of isolation, the interlocking, and protection. So the main objective is for safety and ensure the system is sustainable. And then with the increasing number of DR installation, our electrical grid is slowly transforming from centralized to decentralized system. So moving forward, we expect to see more distributed generation, not only by solar and mini hydro, but other kind of renewable energy resource, such like biogas and wind turbine. So we also welcome any collaboration with the university or any industrial player for the R&D of the topic that we discussed today. So once again, thanks you for your participation, and with this, I will end my presentation. Any question, please let me know.
Okay, thank you, Mr. Chan, for the very interesting presentation. So
Yeah.
now I would like to open for the Q&A session. If any of the participants would like to ask Mr. Chan about this DR and especially about the solar and the micro hydro, maybe this is a good opportunity for you to ask Mr. Chan. You can raise your hand, or maybe you can ask for the host to unmute your microphone. Okay, I guess there's no more further question. Maybe we can move on to our second presenter. I would like to call upon Dr. Aznan Ezrai Arifin from TNDX Sdn Bhd. So just a brief of his biography. So he worked at the TNVX Retail Division Tagana Sdn Bhd, and he received the BEng Bachelor of Engineering degree in Electrical Engineering from Imperial College, London. And further he studied in Master of Science and doctoral degree from the University of Manchester Institute of Science and Technology, UK. Okay, Dr. Aznan.
Hello.
Hi.
Assalamualaikum.
Waalaikumsalam warahmatullahi.
Selamat petang. Very good afternoon to all. Thank you for your invitation to speak at your conference. As you know that we in Kuala Lumpur work at home because of the lockdown. It has been extended yesterday for another 2 weeks, so you can see that I am at home. Okay, unlike our colleague from Sarawak Energy just now, I can see clearly that he is working from the office. Okay, so that's why you see I'm in my room, so I have to speak about maybe 15 minutes, right, on the topic of renewable energy integration, the need for a smart grid. So can I share now?
Yes, sure.
My presentation. Okay.
Yes. Let me share your presentation.
Okay. So again, thank you for the invitation to speak. I'm sure that the invitation came to some of my colleagues in Sarawak Energy. Okay, thank you for those who are listening in. I know some of them from the years, over 20 years of working in TMB. Now I am with TMBX, a subsidiary of TMB, which a subsidiary that specializes in behind the meter products and services, including renewable energy and conventional energy, energy efficiency, solar, EV charging, demand side management, or those are the things that what we call behind the meter and the new utility business. So TMB now has to move. We think that we need to move to those space. So I am in that subsidiary that actually specializes in that kind of products and services. The subject of my talk today, which kind of overlap with what I'm doing now, is renewable energy challenges, the need of a smart grid. I hope that complies with the conference theme. It's not that I do this every day because I'm more of a commercial arrangement now, signing power purchase agreement of solar rooftops and demand side management. Okay, but this is something that I always hold close to my heart, and I keep track of what the developments in TMB and around the world with regard to the need of a smart grid for integration of renewable energy. So let's look at, remind ourselves, if some of you do not know, in Peninsular Malaysia, we have a target of 20% renewable energy by 2025. This is applicable to Peninsular Malaysia, and I think it's applicable to Sabah as well. Maybe not to Sarawak. So we have a target to achieve 20% of renewable energy mix by 2025. So as you can see from the presentation, we are about In 2018, 2%. Now we have to move to 20%. In Peninsular Malaysia, our generation are mainly coal power plants and gas power plants. We have large hydro. We have small hydro. Solar are not that much. But we are developing slowly. I will show you what we have achieved for the past couple of years. So we wanted to move from all of those conventional generation into renewable generation. If you read the news, our CEO of TMB recently announced that the 2,000 megawatts coal power plant in Negeri Sembilan called Jima East is the last coal power plant that TMB is going to build. I'm not sure last for how many years, but we announced officially that it's the last coal plant. So after this, it's going to be completely renewables. Maybe a bit of gas peaking power plant, but going to be renewables. And I think overlapping with this conference, there are Singapore International Energy Week now, this week in Singapore. And I think there will be an announcement of some of an import from Singapore, from Peninsular Malaysia, about 100 megawatts of power, green power from Peninsular Malaysia to Singapore. So that is all interesting development. The next slide shows what we have achieved over the years, 2012 until 2019. The one that we have achieved are solar, especially penetration of solar, large-scale power solar. We have 3 bidding exercises: solar LSS1, large-scale solar 1, large-scale solar 2, large-scale solar 3, and now we are going to LSS4. So these are farm-type solar plants. You will be those that win the bids will be paid. I'm not sure now what's the latest price. Maybe in less than 20 cents per kilowatt hour now. So these are large-scale power plants. So this is the thing that actually facilitate or speed up, if you like, solar power plants or renewable power plants in Peninsular Malaysia. So we have achieved, the number says 100% cumulative average growth rate, 2018-2019. And we also have some installation of biogas, biomass. Not to forget those. Everybody is excited about solar now, but we like to diversify. So I think SEDA still has some allocation of feed-in tariff for other technologies rather than solar. If you have heard also, development in Peninsular Malaysia, we have net energy metering, which I'm going to speak later on a bit more, that we have, it's going to end 31st December 2020. Net energy metering scheme is going to end. So we don't know what's going to happen after that. So all of this commercial, okay. Next slide, I will show you. Okay, so these are the things that has been happening in Peninsular Malaysia. Large scale solar, cycle 4 now, grid connected solar farm, around about 500 megawatts. So the Malaysian maximum demand now before MCO is about, Peninsular Malaysia is about 18 or nearly 19 gigawatts. 19. So compare that to Sarawak, maybe, I'm not sure, maybe Sarawak is about 2 gigawatts, 3 gigawatts, not more than 4 gigawatts. Singapore, maybe 7 gigawatts. Peninsular Malaysia is 19 gigawatts. So to speak of relative terms, we are 2-3 times larger. So we have been developing grid connected solar. There's a bidding exercise now, cycle 4, about 500 megawatts. The other things that has been encouraging of renewable energy penetration in Peninsular Malaysia is net energy metering, about 500 megawatts, December 2020 target of 500 megawatts. So net energy metering, if you all do not know, is about getting credits. If you export solar energy into the grid, you get credits that can be offset with your bills, electricity. You do not get cash. It's unlike feed-in tariff before. What you get is credits, and you can keep the credits for 24 months. So there is a quota, 500 megawatts, that will end December 2020. And we have a scheme called 1-to-1 also, net energy metering, which is interestingly offset exactly the same retail price that you are paying. If you are a B customer at 50.9 cents per kilowatt hour, whatever kilowatt hour that you export to the grid, you will get the same value, 50.9. So that is 1-to-1. So if you are, say for example, in Malaysia, E-tariff, large industry, you get 33.4 cents per kilowatt hour, you pay to TNB. If you export that 1 kilowatt hour, you also get that amount. This is not avoided cost of generation. So that is an interesting development in Malaysia. I think we are one of the first few countries in the world that actually do 1-to-1 net energy metering, which is going to end this December. And so the third point is something that I have been personally involved with, supply agreement for renewable energy. This is something which is what the other jurisdictions call third-party PPA. So this one, any investor, not necessarily TMB, any investor which have capital, which have the expertise, can actually install solar panels on top of one customer and supply the customer underneath. So it is not related to TMB. TMB just only does the billing and metering and billing only. So this is what we call third-party PPA, where a third party can invest, operate, and then at the end of the contract years, transfer the solar panel to the consumers. So these assets belong to the asset owner. They will maintain and operate for a contract years, maybe 21 years. So this is something which is I think this is first in the world, which the utility develop a contract for use by another party to install renewable energy. And because solar net energy metering is coming to an end, we are extensively doing pilots on peer-to-peer. If you have heard about some pilot I announced last year at iGEM about pilot done by SEDA, Sustainable Energy Development Authority. The pilot has been completed. These are desktop pilot. So we have seen how values are being created. So we think that these are exciting times. Those that name may be coming to an end. So afterwards, they may be peer-to-peer, where any particular consumer can sell to each neighbor solar energy from the rooftop. So these are the things that has been happening in Peninsular Malaysia. So these are commercially, this is all for information, which is not, indirectly related to what I want to speak to today. As you know, there are challenges to those. We engineers, as what Mr. Chan mentioned just now about anti-islanding systems protection, these are the things that we need to do. Those are one of the main challenges. So because there are reasons why those are challenges to us, utility engineers, because renewable energy such as there are renewable energy which are controllable and dispatchable, meaning you can control, you can dictate the generation, but there are also renewable energy like solar and wind. We do not really have wind in Peninsular Malaysia, mainly solar, which are non-dispatchable. Meaning non-dispatchable, it is the output is subject to fluctuating weather. So Malaysia has a lot of sun, but also a lot of clouds. So these are intermittent and variable. And the high penetration of this variable energy will present new challenges to the grid. We know that the more the 20% target which has been set by the ministry is a challenge. Commercially, it's a challenge also because you need to get capital to do these projects, and also technically because they are variable, and it is related also to something called lack of inertia. When you have more renewable energy into the system, these systems are mainly DC to AC system through an inverter conversion system. This inverter doesn't have a rotating mass. So it is not as before where you have rotating mass. Big generators that actually maintain the system equilibrium or stability with one another. Now you no longer, or you have less and less of that. The system becomes inertia less. So these are the challenges. I'm going to explain more about this, hopefully. So like I said before, number one challenge is when you have large scale power plant, variation of output up to 80%. Okay, it's good to have solar. Everybody is excited about solar, but they are variable. They vary with cloud cover. So we have seen cases where the large scale power plant actually drop its output to 20% in an instant of time. So cumulatively, this poses risk to security of the system, and mitigation must be implemented. We have to plan for this. So there will be generators, the conventional generators mainly that are on standby, not standby, on spinning reserve that actually has to come in whenever this large scale power plant, large scale solar actually drop its output. Frequency control will be challenging with higher penetration of LSS and distributed solar in the system. These are inverter systems, they do not have rotating mass. Okay, so frequency is a challenge. We have heard, if you Google the news, there are blackouts in Australia, in UK before, a couple of years ago in UK, Australia, and a couple of months back in California, and they were blamed supposedly to renewable energy. So the proponents of renewable energy, it says that it's not because of renewable energy, but those that oppose renewable energy says that it is caused by renewable energy. Okay, my personal opinion is partly also renewable energy because we do not really understand the operation of whenever you have big penetration of renewable energy, you do not know. We haven't got that experience to know enough about renewable energy. Same like 20 years ago when I started my career at TMD, when gas turbines started coming into the system. Before we have oil, we have oil power plants only, and suddenly we have a lot of gas power plant. Okay, that time also we were just trying to understand the behavior of gas power plants also when there was a few blackouts because of lack of understanding of behavior of gas power plants. Okay, so next challenge is ramping. Okay, if those who are in renewable energy know that these are the famous dark curve. So if you have a lot of renewable energy, then you have a phenomena called dark curve. So during peak sun hours, so the generation, the net load will drop. The generation, we have to withdraw some of the conventional power plant because a lot of generation coming from solar. But when during evening time, when you do not have, when the solar actually withdraw, now a lot of ramping has to be done among conventional power plants. So the higher the solar penetration, the higher will be ramping needed, and we have to prepare machines for that. No base load power plants like conventional power plant like coal, the huge coal power plants that we have cannot do this. They are base load plant. So we have to prepare gas power plants that actually ramp up when the solar is coming down and ramping the conventional when the solar is coming up. So the other thing is about frequency stability, displacement of conventional synchronous generator leading to what I mentioned before, smaller inertia. Now, inverters do not have rotating mass component. Those in power system specialty knows this pretty well, where if you have less rotating mass now, so there will be no headroom for there will be lesser governor control. There are no governor control for low frequency incident. So now because now there's no rotating mass that actually holds the system together. So it's more like voltage control rather than frequency control. So loss of generation, the bottom frequency will be lower with higher solar penetration. So if you have a large percentage of solar, the bottom frequency, whenever there is a loss of generation, the bottom frequency will be lower than before. So we have to put all sort of protection or spinning reserve to recover this. And finally, the last challenge is voltage stability, displacement of conventional synchronous generator, voltage regulating, stabilizing AVR, auto voltage control. Voltage regulation becomes difficult in high penetration of renewables because for a similar fault, like before, a wider part of the grid will experience voltage dip. So that is something that we are beginning to understand. The behavior, the dip, and also the frequency bottoming out before will be lower now than before. whenever you have a fault, the voltage will be lower than before because of high penetration of renewable energy. So the next few slides are how do we mitigate all of this? Number one is what we need to do in Malaysia. What we are doing in Peninsular Malaysia, we have to improve grid code. So the grid code has to be added the part of requirements for conventional generation. The grid code that we designed before, Peninsular Malaysia has a Malaysian grid code. It was designed for the old conventional system. So we need to look at it. Okay, there are some effort in looking at it and then trying to address the requirements to grid code. Frequency response, reactive support using low voltage event. Interconnection is important. Okay, we should know that for a system with high penetration of renewable energy, it is of an advantage to have interconnections. We have in Peninsular Malaysia, we have connection with Thailand, we have connection with Singapore. So the bigger system, the bigger rotating mass, so is better for us in terms of stability. Sharing on spinning reserve for intermittency and forecast error. So interconnection is important for high penetration system of renewable energy. Operation improvement that we need to do, we need to reduce the dispatch interval. Before we dispatching generator megawatt by 30-hour slots, now we have to lower than that. We have to put advanced, sophisticated renewable forecast system. We need to forecast our solar. I saw one of the slides that Mr. Chan showed about solar generation, irradiance. So we need to have that in real time to show irradiance in real time. The other thing we need to do, we need to diversify renewable portfolio. We cannot only simply depend on solar. We need to diversify. Do not just concentrate on solar. Solar is the easiest to do, but let's do biogas, biomass. Maybe those are dispatchable. Number 5 is electricity market and trading. Okay, Malaysia, Peninsular Malaysia is highly vertically integrated still. There was an effort before to actually open up the market. So the literature says that you need to open up the market, be transparent electricity market, power trading locally and regionally. There's something called MESI 2.0 before that was worked out before, but still now because of change of government, they put on hold. So that's the thing that we can do to enable integration of more renewable energy. And finally, we have to plan and design in the future for a system which is flexible. Flexible power system can modify electricity production or consumption in response to variability. So this flexibility is like spinning reserve before. So when the system is able to, when the system is flexible, whenever the renewable energy drop out, like solar has cloud cover, and other system will come to replace it. Or you can do it on the supply side. Whenever there is an excess in solar, for example, let's do a lot of consumption. So let's start up all our appliances, all the consumptions must increase. But whenever there is solar drop or intermittency or variability of solar, the solar generation irradiance actually drop. Okay, let's also look at demand side, how we can actually cut off load, like demand side management. So these are the things that we need to do to enable higher penetration of renewable energy into the system. Okay, so the other things on the smart grid things, some of these I already mentioned. So we need to have a smarter grid. A lot of people has been discussing smart grid before. Okay, some people know. So what is smart grid? My understanding of smart grid is they have two-way flow of information and power. There's better coordination, a lot of IT, a lot of control, communication. So some of the things that I listed here, like the things that we need to do to enable smart grid, therefore to accommodate more renewable energy, like dynamic line rating, the rating, the transmission line mega capacity must be dynamic. It is probably with a temperature sensor that you cannot be a static rating, so enable more power that flow to a line, because some of these power plants, renewable energy power plants are remotely connected. Demand response, I mentioned just now, enabled by smart meters and intelligent loops. The customers must be incentivized to actually drop the consumption whenever there is less generation from solar plants, for example. Smart inverters and other advanced controls. The grid code, Malaysian grid code now, Peninsular Malaysia grid code actually impose smart inverter requirement. So this actually can reduce the need for significant grid transmission and distribution upgrade because the inverter now is able to control the voltage more intelligently rather than before. Storage, somebody mentioned just now, yes, we are looking at it, but the main problem about storage now is the cost. Per kilowatt hour is very expensive. So there are some pilots in TMB system, but it's still an expensive scheme. We have to look at other revenue streams. We need to enable the business case for planting grid scale storage. Grid storage is good to enable more integration of renewable because it can firm up renewable energy like solar, but still the price. Regulatory wise, we are not able to put it in a regulated asset base because we need to a return on this investment. Behind the meter storage is something that customers need to do. Advanced energy management systems, we have to put up more better control system, better forecast, better visibility on our operator. And finally, again, I've been repetitive, better forecasting. So I think a few more slides, okay, regarding a lot of solar coming into the system. How to host more rooftop PV is by having grid monitoring and management. We have imposed the requirement to have SCADA system. If the solar is more than 1 megawatt, probably the value is going to go lower and lower. Local flexibility, inverter standards we are imposing. Grid investment, we have to invest more. People say that you have solar, why you need to invest more? Actually, we have to invest more on the intelligence of the system because we have to accommodate, we have to be smart, we have to be able to see those solar generation. Managing PV exports. So there is a requirement, there's a limitation now in TMB, for example, that you cannot install more than 75% of maximum demand. So those are managing PV exports. You do not want to disturb the system so much. So other thing that you can do as distributed energy resource management, these are, people have been calling these terms, a lot of software that has been bandied around. Okay, so these are just monitoring system to see how the local integration or penetration solar, what's the kilowatt hour, what's the megawatt hour, what's the voltage. Okay, these are the things that we're doing now in terms of trying to accommodate more renewable energy. Okay, and finally, somebody mentioned, did somebody mention virtual power plant? Okay, let me end by doing, there's a new concept called virtual power plant, whereby there's a party called an integrator, aggregator, then actually accumulate or combine all of these resources, then actually put up a one system to the utility. So this is called virtual power plant. Then you can actually combine all of the local resources and then do a local control system and then offer this value to the utility. This is something also in consideration in Peninsular Malaysia. All of this, I'm telling you, none other than to accommodate more renewable energy in the system. That's all. Thank you very much. I think I've spoken more. I think most of it you already know. I'm just re-emphasizing what TMB is doing, and thank you for your attention.
Okay, thank you, Dr. Aznan Arifin, for the very interesting and very energetic presentation. So, me as a listener, I really feel the energy in your presentation. Thank you for your interesting presentation. So, without further ado, I would like to call upon our third presenter for our second session, which is who is Dr. Yanwar Zul Aryan Shah Arif. He is the senior lecturer from University of Malaysia Sarawak. So currently teaching electrical electronic in the Department of Electrical and Electronic Engineering. Okay, Dr. Yanwar, the screen is yours now. Okay.
Hello, Dr. Anwar, you can hear us? Hello? Dr. Anwar? Can you hear us?
Yes, we can hear you.
Okay. Hello, Doctor? Hello? Dr. Anwar? Hello? You check your sound because no, we cannot hear you. We cannot hear you. Hello? Yes. We are sorry for the audience. Have some technical problem with the Dr. Yanmar. I think he will maybe he will solve the problem soon. Inshallah.
From Sarawak, yeah. Yes.
Okay, to all participants, sorry for the technical glitch. Sorry for the technical glitch. In the meantime, I guess I will ask Dr. Yana to solve this problem first, and then in the meantime, maybe we can move to the next presenter. The next presenter will be personnel from Sarawak Energy Berhad, who will deliver his speech, his topics on the Rumah Bada solar project. May I know who will be presenting this topic? Oh, Mr. Ronnie, yeah? Okay. Okay, Mr. Ronnie, the screen is yours now.
All right, I'm going to share my screen now.
Yeah. Yes. Go ahead.
Okay. Yep. Very good afternoon to the audience. My name is Ronnie. I'm from Sarawak Energy R&D departments. Yep. And this is my title actually. I'm going to present some CSR solar project at Bada Air Sarawak. Rumah Bada is one of the solar project has been implemented in Bada Air, which is throughout this CSR program. CSR is meaning that corporate social responsibility, which means that all the solar cost project is being fully supported by Sarawak Energy. And then we also get community to involving in this project so that they can helping us to do some like silver work or doing some material shipping works. The involvement of the community is helping a lot on this work so that we can work together as a team to complete the solar project. Well, I think some of the audience should be familiar with this Sustainable Development Goal, and which was promoted by United Nations. And there are 17 goals. Well, if you notice in this slide, which is SDG number 7, landed affordable and clean energy, is one of the goals which I think Sarawak Energy can contribute a lot from here. As utility company, Sarawak Energy not just provide electricity to end user, but we are actually looking for affordable and clean energies and provide the best energy solutions to all the Sarawakians. Sarawak Energy really put a lot of efforts to provide electricity to urban user, but we also looking to provide the electricity supplies for the rural community as well. So you can see from here, there is a list 1 until 9. This is the outdated list which we successfully energize the solar system, off-grid solar system at Bada Air, Sarawak. So the most recent is Rumah Bada, which is around 31 kilowatt solar system. And one of the challenging I would like to highlight is due to the logistic issue. Those villages is scattered around all the Bada Air reservoir. So there's no road access to be reaching there. That's one of the challenges we're facing. So the conventional one, if I'm using the conventional overhead line, it's not so feasible to be implemented. So one of the solutions we try to introduce is by using the off-grid solar system to provide the basic electricity for the rural communities. And off-grid solar system, it can provide basic electricity to them while waiting for the road access or other infrastructure to be built. So upon the completion of these works, those solar systems able to provide 24 hours free electricity without bill, without tariff to them. It means a lot to the community, and eventually it can further improve their community lifestyle. And in this next slide, this is the solar home system. I would say that this is the first innovation work introduced by R&D department Sarawak Energy, which our main goal actually is want to provide the basic electricity for rural communities. So those solar home system, it means that each household will have their own solar system, means that they have their own inverters, they have their own solar panels, and the solar panel is mainly on the rooftop structures. So it will be equipped on top of the rooftop structures. And it really can provide basic electricity and small electrical appliance usage. And we also designed the solar freezer system. Basically, it can helping the community to keep their fresh food, especially the fish, which they can harvest in Padang Air. So with more electrical devices can be used, it brings more convenience to rural communities. And this is the regarding of the centralized solar system. This is actually the second generation solar system which implemented by IIT departments. We do some study on the solar home system. We found that there may some gap or improvement to be improved throughout the solar home system. So centralized solar system is being introduced for bigger household, maybe more than 10 household. So those household we will introduce a solar centralized system. And typically the design is come with 1 kilowatt peak per household. Maybe let me take an example. If let's say there are 30 households, we'll provide 30 kilowatt peak solar panel. And Sensco inverter sizes based on the household. And we will provide 3-day autonomies and with 3 kilowatt per day per household as the energy usage. And each household, they will be equipped with the energy limiter. The main purpose of this energy limiter is to limit the energy usage with 3 kilowatt per day per household as a protection for the solar system. And you can see from here, this is some of this example of the energy storage system which we use throughout the Padang Air solar system. Majority of system we are using lead acid battery, which you can see on the picture right side and also the bottom right. So lead acid is, in terms of the capital cost, is much cheaper than lithium ion, but in terms of the lifetime, it might be shorter. So we're also looking forward alternative energy solutions, which we're looking for lithium ion. We do deploy one of the solar site by using lithium ion battery as the energy storage system. Yeah, here are some of the prototypes which we can see what's the involvement for the committee. They actually help a lot of and commit themselves to complete the solar project. They do helping to carry out the equipments, for example, like inverters, which you can see in the picture on the left-hand side. They're also helping to carry out the panels, shipping the panel to the rivers by using the longboard. And we do also provide some personal protection equipments for them. And you can see from here, they do helping us a lot to do the maintenance work for the inverters to clean out the dust and to perform some land clearing works before we implement the concrete work. Eventually, this solar system will be handed over to community. So community be provided basic training so that they can at least provide some basic maintenance works. We do provide them some demo on how to clean the solar panel so that they can plan ahead the routine maintenance works so that it can keep the system in the best efficiency. And we also provide some training on the main switchboard to reset the system and to provide some inspection work on the solar system. And basically, the minor maintenance work will be handled by the community. So But when there's a major breakdown occur, definitely our SEB technical team will go inside to start to rectify the issues. And this is one of the slides which I would like to stay here for a longer time. We like to highlight type of R&D work to be done throughout this few years. So basically, we will highlight point number one first, which is regarding our system improvement. As I showed in the previous slide, which we eventually our design is coming from solar home system for smaller household, and then we come up to the centralized system. And we found that the solar home system, they're lacking of, compared to the centralized system. Centralized system is much more efficiency in terms of system, and it's more easy to be maintained. And centralized solar system will have more protection system, such as lightning protection system. They have their own powerhouse to isolate the unauthorized person, such as the children. And then we have managed block before the outgoings. So those are the protection be further equipped in centralized system. And then it really helped a lot to helping us to do the maintenance work. When eventually we found out that like solar system, if there is faulty occur in the inverters, we need to send our main powers to going down to the site. And with using the centralized system, it's much more easy to maintain because we only need to take care of one of the solar system in one of the villages. And point number two, which I'd like to highlight, is on the technology deployment. We do try our best to look for the alternative solution to be used as an energy storage system for solar or grid solar system. And we do introduce using lead acid and lithium ion. And of course, lead acid, they have their own disadvantage and advantage. Lead acid is much more, in terms of lifetime, it can last for 2 to 5 years and is corrosive. So it needs to be properly disposed once it's reached to end time. Whereas the lithium ion can last for a longer period, and it requires smaller footage area, which because of it has higher energy density than lead acid battery. But one of the advantage definitely is it require a bigger capital cost to implement the lithium ion batteries. And point number 3, I'd like to highlight regarding on the energy optimizations. So optimization study is required to be conducted in a couple of months, and we need a lot of info for existing solar system. First of all, like the data log from the inverters and some information from the energy storage system. And we do manage to do the analysis and evaluation based on the existing data. And one of the interesting things that we managed to find out is we do encounter that some of the portion of energy coming from the solar panel is being wasted. And it means that, put it another way, it means that we can utilize it if we successfully harvest those wasted energy. So from the analysis, we found that this smart inverter, it actually cut off the input power of the solar panel. When the energy storage is fully charged, it's already fully charged, and also the load demand is quite low. So this is, we do some research work on this, and then we try to figure out how to optimize the existing system based on this issue. So we do increase, from here, we do increase the load demand from 2 kWh per household to 3 kWh per household. Basically, it's helping the community to have more energy access to using the electric device. And also, when we implement this status, technically, the state of charge of battery will have much more lower, and it allows more solar power to be charged during the noontime. So, yeah, we're still working on that. Hopefully, we can find more innovation work throughout this project. And then you can see from here, some of the advantage benefit be introduced to community. So as you can see from picture on the top right side, children, they can access the electronic gadget. Well, before implement this solar project, I feel quite sad, when I saw those children that cannot enjoy the electricity supply just like us in urban area. So by introducing this solar system, it really can provide the basic electricity to them, and then they can do the homework they can study together. Eventually, I believe it can improve the education level of their children. For adult, you can see on the picture bottom left side, they can have more time to perform their works. They can repair their fishnet, they can do some handicraft, and eventually it can generate more income. Then, of course, for children and adults, they can enjoy more entertainments. They can enjoy the TV without needed to start a diesel genset, which is really costly in terms of the operations. And last but not least, they can do gathering during the nighttime and build out the stronger relationship among them. Yeah, here are other photos which I like to slide. Yeah, that's all for me. Thank you.
Okay, thank you, Mr. Rodney, for the very interesting presentation. So I would like to open up for the Q&A session. Do you have any question regarding the Rumah Badah Solar Project? Okay, if there is no more question, I will proceed with our next presenter, Mr. Patompong Bunsiri from Provincial Electricity Authority, PA, Thailand. Okay, Mr. Patompong, are you here?
Hello, have you hear me?
Yeah, we can hear you very clear.
Okay, wait me a second. I gonna open the file because okay, I'm ready. Can I share my file for now?
Yeah, sure, I can.
Okay. Okay. Okay, for now, can you see my presentation?
Yes, very clear.
Okay, thank you very much. Okay, can I start for now?
Yes.
Okay. First of all, today, my name is Patompong Bunsiri. I'm on behalf of PEA, Provincial Electricity Authority. I'm an electrical engineer in Provincial Electricity Authority in Area 1 in Chiang Mai. I graduated Master of Degree Future Power Networks from Imperial College London by the PEA scholarship. Today, I'm gonna explain show the presentation about the design and real case study of PEA's microgrid at Ban Khun Pat Village, Chiang Mai Province. This is the first microgrid in Thailand. It's like the full-scale microgrid. It's an AC microgrid that consists of solar panel, hydro generator, and storage, and connected with the grid. Okay. The background of the PEA. PEA is a state enterprise belong to the Thai government, and we have the service area as around 510,000 square kilometer or coverage 99% of Thailand, and we split to 12 region office, and we have many places to look after, look like the forest, like a isolate area, like a industrial area or the urban area. We have we have customer, it's around 20 million customer, and our peak demand is around 20 gigawatt in May 2020. Kunpat Village is a project that integrates between microgrid technology and the social enterprise for sustainable development. We consist of the power technology, power system technology, included the social enterprise that mean we sharing the water that I'm gonna explain you later. Okay, Ban Kunpai is located in Chiang Mai province. It's far from the substation of PA is about 35 kilometers, and we have customer to service around about 500 households, and mostly people they work like agriculture, and the landscape of the Kunpat village is mostly the high slope area. And this one that we from this one we have the rear, we have the reservoir, but we have to share the water with the local people in there, because if we have the just only a mini hydropower, it's gonna be separate power and use the water. And the people who live in the top of the mountain, they cannot use the water. That means why we have to sharing the water. That's called like the cooperation with the people in there. We improve our reservoir, and we have the water storage for water storage for water supply to the customer in there, and we have distributed water storage for the agriculture in that side, and we have distributed water pipe for agriculture side that make us can live with the local people in there. And after that, we have the project to improve the efficiency of the hydropower. We collaborate with the AIT to improve the hydropower to have more efficient performance by using the turbo turbine that made by the Thai people. It's the first one that made by the Thai people, and we have the SCADA remote control that can control by the SCADA center in Chiang Mai, like remotely. And after that, we have the mini hydro, but the capacity is not enough for the load in there. We have the project to install the distribution network to the Kunpat village, but the distribution system is located and pass through the forest and pass through the tree, and it make the distribution network collapse very easy. This is the reason why we have to use the microgrid system to improve the system that far from the substation and look like the remotely, like a far from in the Icelandic site. And we have in this area, we install 100 of batteries energy storage to store energy in that, and we have the main source from the solar cell about 100 kilowatt, and we have 4 switches for load curtailment to cut off the load during the Icelandic mode, because during the if we decide the microgrid, decide the DG matching with the equaling to the load, it's gonna be use a lot of money. This is the reason why we use the load curtailment to maintain the load management in there. And we have HMI screen for the microgrid that we can control from the Kunpat side, Kunpat microgrid side, or we can control SCADA mode remotely from SCADA center in Lamphun province. And in here is a schematic overview of the microgrid in here. We have the PA microgrid controller. We can do the grid connected. We can do ice landing, smooth changing mode. And we have a backstart by using the battery. And I'm gonna show the case study after that. And we have load shifting and peak shifting. and we have PV smoothing and load shedding. In this picture, you can see like the powerful direction between the BESS battery energy storage system and the system. It can have bi-direction, like charge and discharge to the system. It can charge the power from the solar during the daytime, and it's gonna discharge the power during the nighttime that the solar cannot produce energy. In here is a single line diagram for this microgrid. This microgrid has the communication by using the fiber optic, and also every single load-based switch and every single equipment controlled by IEC 61X0, and we have the function to synchronize like in millisecond. It during the changing mode, it's gonna be like really smoothly. And this one is very important. Is the supply duration for BESS battery energy storage. We split the supply zone to be 4 zones, and zone 1 is very important. If zone 1, if the generator cannot supply the power to the system and have only BESS or battery, it can supply to zone 1 greater than 24 hours. That means it have energy sufficient for supply to the customer in there during the emergency event. And this one is the diagram that shows the operational characteristic of the microgrid during the sufficient water. That means the mini hydro can supply the power reaching to the maximum capacity. That means the battery can charge the power from the hydro, and the hydro can be the base of the system during this condition. But during the summer, or if the people need the water to be the agriculture, we have the mode like a saving water mode to save the water, like a lander distribution, a mini hydro at the minimum requirement, like just only 10 or 15 kilowatt, and it have a little bit duration to consume the power from the grid, and it's mean like we have this mode, because if we don't have this mode, we're gonna have the problem with the agriculture that we allow there. And this one is a levelized cost that we can compute by using the Homer program. For now, the system microgrid system levelized cost is allowed 3.5 baht, or it's like cheaper than the grid, cheaper than the grid price at there. If we convert to the dollar, it's allowed $0.117 US dollar. And this one, we can save the gas emission for our work is allowed 40,000 baht per year. And this one, how can we the method that we use to design the microgrid at here, we use a Homer program by using the resource from the Big Silent program and PV6 program that we have the license, that PA we have the license. Another program we don't have the license, and I think the Homer program and Big Silent program and PV6 is very useful to and compatible to use to design the microgrid. And this one is the method to compute to design the microgrid at the Kunpai village. First of all, we have to design the load profile by using the customer demand at there to 24-hour load characteristic, and after that we have to use Big Silent program to design the existing power flow. To this one is very important because we can use this one to do the load curtailment And after that, we have to know the energy resources data. Energy resources data that from compute by PVSys, and we have to make sure the hydro foliage at this site. And after that, in the fourth method, we have to know the unit cost for each DG and grid price to compute the financial analysis by using Homer Pro. And after that, we use Homer Pro to design and choose the suitable case from Homer Pro results. And finally, we have to export this one and run by using the compute by using the excellent program to check the securities of supply again. And this one is the result that we have from the real case. This one is not from the program, but this one from the real case. The characteristic of each generation unit and load profile when the solar panel can produce electricity all day. You can see this one. It is like the solar can produce smoothly, and the load is changed. The peak demand is in the morning because the local people normally use the load like to cooking in the morning. And this one show that the power from the solar is very unstable. In fact, fluctuated because of the cloud. That means you can see we have to maintain the system by using the hydropower. And this one show that the solar is very unstable, and hydropower have to produce energy more during the unstable of the solar panel to this one for supply the load, supply the power to the load. And this one is case study 1, load shedding. As you can see in the figure, at the 6:30 a.m., all customers in microgrid will still supply the electricity after the collapse of the system because we have the battery to supply the load. And after that, 6:35 a.m., after the BESS SOC of BESS is lower than 30%, switch 2 and switch 4 that controller that used to cut the load at zone 2 and zone 4 will open and reduce the discharge rate of BESS. This is for store the electricity for priority areas. And after that, if you see in here, 6:40 a.m., BESS was recharged while the sun rise. And at the 9:46 a.m., the SOC of battery was reached to 70%. PV was commanded to reduce its output because it light load. And this one is export from the SCADA in the Goodbye village. And after that, the case study 2, a comparison of non-PV smoothing and PV smoothing. On the left-hand side, you can see the voltage in the red graph. The voltage is very unstable because of the cloud is cover the panel. But in the right-hand side, we have the PV smoothing. The voltage is very stable because we have the function of that. And this one, case study 3, backstart. We use the battery to be the backstart generator. It start to supply electricity all generations is then reconnected. If you see in the figure, after we have the grid is collapsed, the battery will be the backstart generator, start to supply electricity for other, and then S1 was opened during the interruption on PA main grid. And after that, if the main grid is reconnected, the PA main the S1 will be reconnected to the system because the main grid is come up. Case study 4, SCADA control. We design the SCADA control by using the load characteristic in there. The battery will be charged during the sunrise and will be discharged during the during the peak demand and also after the energy after the sunrise. And during the daytime, if there's cloud is so much, you're gonna use the function of PV smoothing. And this one is export from the SCADA system of us. Okay. The last one, case study 5, is the operation of battery storage system during the islanding mode. In this case, we see that the dark red one is the SOC of the battery. The SOC of the battery is lower, is decreased all the time because it supply the power to the system during the all generator cannot support the power, and and this graph it can show that the uh, the the solar panel cannot produce the power. That means the main actor is the battery for the microgrid in the back village. Okay, this one is just only the one of piece of the case study in the Kunpat village. After that, we're gonna have project to have more deeply design and deeply classify and cooperate between the machine that have the low inertia and the inverter that have the fast inertia to matching together, and we're gonna see the cooperate between of two devices. Okay, thank you very much.
Okay, thank you, Mr. Patupong, for the interesting presentation. Now I would like to open the Q&A session. I think there's one question from Mr. Muhammad Jamil. He asked, in terms of time, how durable is the PV solar cell and battery?
Sorry, what a question? Sorry.
There is a question from Mr. Muhammad Jamil. He asked, in terms of time, how durable is the PV solar cell and battery? So, I couldn't hear your voice, Mr. Patupong. Your voice is not clear. Okay, maybe I can just write down the question from Mr. Muhammad Jamil at the chat box. So I post out the question from Mr. Muhammad Jamil in the chat box. Mr. Patupong, your video and your audio is has a bit of lagging. Maybe to answer the question, maybe you can just type in the answer. Mr. Patupong, can you hear me? Perhaps you can just type in the answer for Mr. Muhammad Jamil.
Maybe you connect to mic, the microphone. You can hear us?
Okay, I think perhaps just to save time, perhaps maybe Mr. Patofong can type in the answer. While we move on to the next presenter, Mr. Muhammad Jamil can read out the answer from the chat box. Huh? Okay. So we will move on to the next presenter, the Dr. Anwar. Dr. Anwar, I think he just messaged me that he already solved the technical problem. So maybe we can call upon our next presenter, Dr. Anwar.
Hello, Assalamualaikum warahmatullahi wabarakatuh.
Okay, Dr. Anwar, now the screen is all yours. Huh?
Okay, try to share again my screen.
You can share the screen. Okay.
Could you see my slide in your screen?
Yes,
yes,
very clear.
And my voice now?
Yes, very clear.
Okay, thank you very much. I'm so sorry about the previous technical program. So can I proceed now?
Yes.
Okay, thank you again for very good afternoon for all the panelists, presenter, and participants. So I would like to share the topic entitled with palm-based external fluid as alternative biodegradable transformer oil application. My name is Yanur. Okay, as we know, power transformer one of the important equipment in transmission and distribution system. For example, to step up the voltage level in transmission line, and then to decrease the voltage level in main distribution, also in the low voltage level. So for oil type insulation, oil type transformer, commonly they use mineral oil. The function is for insulation and for cooling purpose. So illustration of the core winding in the power transformer can be seen here. If we zoom here, we can see the low voltage level, low voltage winding wrapped by kraft paper insulation, and also in the other side is the high voltage winding. And this core and winding immersed in the insulation oil inside the tank. Properties of good transformer insulation oil, they have to have some properties such as high dielectric strength, low viscosity for cooling purpose, and good aging behavior during the service, and have high flash point for safety. And currently increase the concern about the environmental friendly system, so the type of biodegradable oil also increase. So the slides give the brief history about the vegetable-based oil. Start around 1990, the research, and then this is commercial product of vegetable-based oil, soybean-based oil, with different manufacturer, and this is from Cooper. They call as FR3, and the other one Biotem, produced by ABB. And then PFAE, palm fatty acid ester. This is palm-based oil. This is produced by Lion Corporation, Japan. And this is produced by MPOB, Malaysian Palm Oil Board. The technical name is highlight oil. Okay, breakdown in power transformer due to insulation failure due to mineral oil can be the source is the properties of mineral oil have low place point, so easy to cause a fire. Non-renewable resources will run out in the future, and then the properties of non-biodegradable. It could spill or leaking may contaminate the water and soil. So the alternative, more environmental friendly palm oil is the vegetable base with having high plus point and renewable resources, fully biodegradable, high electric strength compared to mineral oil. But the weakness of the vegetable oil is attractive to the moisture. And in this research, particularly Malaysia, Indonesia, and some Southeast countries, we have palm oil agriculture, and so they introduce palm-based oil as power transformer oil. For example, for silk condition, this is not studied yet widely, and for practical or surface transformer, not been tested. So this is some review about the type of transformer insulation oil. It can be divided by two main types, non-biodegradable and biodegradable. Non-biodegradable, it can be mineral oil. This is widely used in the existing power transformer oil, ascarols, another type, HMWH, high molecular weight hydrocarbon, and this is the synthetic one, silicon oil. And the biodegradable oil normally is ester-based oil. It can be synthetic or natural ester. Produced from vegetable oil. With the two types of natural ester is triglyceride ester and monoester. Degradation process of the oil and also pepper. These two types of insulation inside the power transformer. It's in insulation oil, for example, mineral oil is due to of the oxidation process. There is oxygen inside the oil due to the aging, spark, and any fail inside the transformer oil. Also in vegetable oil, there also oxidation, and the other one hydrolysis due to of the water content. So the properties of fatty acid can be saturated and unsaturated. And for insulation paper, there's three kind of degradation process due to the heat during the surface. It's thermal and oxygen, also oxidation, and also water. How do we make assessment or measure the performance of transformer? For oil, there are some tests or observation that we can perform. For example, by visual examination, we see the oil itself by the color, and we can measure the viscosity, kinematic and dynamic viscosity. And for the electrical properties, we can test the breakdown voltage or the electric strength, capacitance, power pressure filtration, TAM, total acid number, and also the GA, the salt gas analysis. And paper also related with this, can be associated with this test. And for transformer itself, can we perform capacitance test, PDC, polarization and depolarization current, and also dissipation factor. Okay, according to the standard or technical specification for insulation oil, it can be divided into the three main properties: chemical, electrical, and physical. In physical, for example, from the visual observation, you can see two type standard with different type of insulation oil. Mineral oil is the for the existing one. Based on this IEEE standard number, and for vegetable based oil with this standard number, we can see, but in surface there is no strictly standard for that. But for all of the standard, they give the same value, at least for the AC breakdown level. I have to more than 30 kV. According to IEC 60156 standard electric test. Okay, for DGA, dissolved gas analysis, there are some combustible gases which can be interpreted for the some defect or failure in the transformer oil. For example, the availability of hydrogen, methane gas, ethane, ethylene, acetylene, carbon monoxide, and carbon dioxide with a certain level of ppm can indicate some failure. For example, the partial discharge activities, water content, aging, and so on. So now, what is the nanofluid? The nanofluid is consists of nanoparticle suspended in a liquid medium, and the particle size is less than 25 nanometer. And nanofluid will be prepared by mixing the nanoparticle for various concentration with base fluid using some step, like we will do the using magnetic stirrer, sonication process, and then drying in heating oven, and etc. The advantage of nanofluid, they have great thermophysical properties such as thermal conductivity, thermal diffusivity, viscosity, and heat transfer coefficient as compared to the base fluids. There's some literature conducted by researcher who deal with this investigation. For example, they investigated the breakdown properties of transformer oil-based titanium nanofluid. They do some tests, and I go directly to the methodology. They do the breakdown, and then they also measure the relative permittivity and resistivity test. And they found that the new type of transformer oil was developed. They make some modification from the original transformer oil and introduced by nanoparticle titanium to enhance their electric performance, and also comprehensive comparison of breakdown properties between mineral oil, the original one, and nanofluid were carried out in this experiment. So the main finding, as can be seen in this table, the original transformer oil have the mean breakdown voltage in this level 71.59 kilovolt, but after added by concentration of titanium 0.06 gram per liter, it can be increased up to 62 or it's 82.48. This is the optimum, but for this concentration decrease, and also this is decrease, so this is the optimum one. So it's found that there is agglomeration of particle may happen when the concentration of titanium approach saturation. So there is some level that we have to notice that by adding exceed the amount of the nanoparticle will give the drawback, not increase the breakdown voltage level. Another researcher, instead of titanium, they test with the nanosilica, and then observe the breakdown voltage and also viscosity. I would like to show you the result. You can see here there are two different concentration of nanosilica, 0.01% in this brown histogram, and the yellow one 0.02, but with different humidity. With the increase low humidity, the SE breakdown also increase. With the higher concentration, they have the higher breakdown voltage. And last researcher, they do with vegetable-based oil under AC voltage and also lightning impact voltage. So they conduct with let me check here. This sample material oil is from this manufacturer and that's Nitrolera. And then they do AC breakdown test according this standard, IEC 60156. And then the main finding, they can have the tendency increasing of the voltage level in the sequence of the AC breakdown voltage. They have around 40 sequence, the repeating breakdown voltage test with the single oil sample. So if there is reach steady state after about 10 sequences, this is their main result. So what we have been doing here in our lab, we try to develop also palm-based ester nanofluid. First, we perform the palm-based ester, which means the palm oil, pure palm oil. We make we conduct esterification process in the lab. We add potassium hydroxide, and then we stir, and then we mix in 60 minutes, and then we pour the mixture into spaghetti funnel, and we take the we will have the ester product from the palm-based oil. And then in order to check the performance, the ester that we have found, we conduct aging test. We put the sample inside the thermal oven with different aging time. For example, this is unaged, 50 hour and 150 hour with the temperature is 100 degrees Celsius using this thermal oven. And then we will find this from the visual inspection. There is clearly different from the color of the ester. And for the pure palm oil, there is no significant look like same. But we conduct the different tests. For example, breakdown voltage test. And we find palm ester look like a constant, and for the pure palm oil is increased during the aging time. This is mainly due to of the we consider the reduce of the water content due to the aging process. So as a consequence, we have the higher breakdown voltage. And then for kinematic viscosity, we found ester have the better viscosity compared with the palm oil, the pure palm oil. For total acid number, this is mineral oil, the existing one, and this palm oil, and the gray one is our ester. It's like the second lowest compared with other sample oil. And for water content also we can see here for the blue here mineral oil, and this is palm oil, and this is our methyl ester is in the middle of the water content. So as conclusion, we found that the result give as initial step to have the better alternative solution oil which provide excellent electrical properties while also being environmentally friendly. So we need some other tests, for example, for the longer aging time to see the performance of the oil. And besides, we also we need to analyze recap very small window for the experiment to produce a rather cost-effective yield in terms of the esterification and so on. And our next step, we will introduce the palm-based nanofluid sample by nanoparticle. In this step, we already provide nanosilica and also nano zinc oxide. And then we will investigate some properties under thermal aging, like breakdown voltage, kinematic viscosity, water content, total action number, flash point, and also DGA, isokinesis. And after we find the better or the best solution or the sample, we try to introduce the sample in real power transformer application, and then we observe the performance during the service. I think that's all for my sharing. I return to our host, Dr. Hazrul. Thank you very much.
Okay, thank you, Dr. Reno, for the very interesting presentation. I would like to open now the Q&A session. I invite all the attendees to ask question if you have any question regarding regarding this topic.
Yes. Yes. Hazrul?
Yes.
This question to me?
So far, not yet.
Okay. I thought that there is a question to me. Sorry. Okay.
Okay. If there is no question, maybe we can move to our next presenter, Mr. Dedi Haning. Okay, Mr. Dedi Haning Mr. Dedi Haning has more than 10 years of experience in rural electrification. So his research interests on PV off-grid management, and currently he is an advisor on renewable energy project to GIZ in Sumba. He is also the director of renewable energy service company Bright Sumba and co-founder of a knowledge platform, Women in Mining and Energy Indonesia. So without further ado, I would like to call upon our presenter, Bapak Dedi Haning.
Yeah. Okay. Hi. Can you hear me? Can you hear me clear?
Yes. Very clear.
Okay.
Yes,
right.
Very clear.
Cool. Thank you very much. Good afternoon, fellow speakers, also moderators and participants. And thank you for the opportunity to talk with this conference. My presentation today will be on the topic of community-based PV management here in Indonesia. And I'd like to share lesson learned that we already accumulated over 10 years time. Okay. Yeah, so just a bit brief about me. I'm currently working for GIZ, also together with UK program here in Indonesia on energy transitioning, specifically on the building up the knowledge management on PV off-grid. I'm not an engineering. I obtained my Master of Business Advanced from Queensland University for Technology. Definitely not in engineering. So if you have any question regarding technical engineering, I will have to keep it and ask the expert on GIS. Much of my work in GIZ has been documented very well on the link. I can share the presentation later on. So to start with the presentation, I'd like to give a little bit of context about Indonesian electricity condition. At the moment, we have already reached 99.90%, although it's debatable between one minister to the other ministers. I can see that the government tried really hard to provide universal access to electricity through mini hydro, PV mini grid, solar home system, and currently they are trying a new system called battery charging station to reach more of secluded communities. So if you're looking at Indonesian map, you know that Indonesia is large, 5,000 kilometers span west to east, and off-grid electrification is going to be a huge task. And specifically targeting what we call three areas. It's remote, secluded, and underdeveloped areas. So apart from being remote and secluded and underdeveloped, these communities are also pure under poverty. So that's why Indonesian government through the Ministry of Energy developed this program launched in 2011. The target is to electrify as much as possible these communities to provide tier 3 of electricity service. And so far we already reached 1,000 villages through AC and DC capacity, DC coupling systems between 10 to 100 kilowatt peak. And we've seen a lot of impact in regard to job creations, additional income opportunities, and also open up more of the secluded village to through provision of technology. And the project itself is working like this. The provincial government provide the proposal to the national government, and the national government will do the tender and also roll out the implementation. After that, the national government will hand it over back to provincial government to be managed by what we call local or community organizations. And the tariff itself, it's regulated between the communities, so they all agreed on tariff, whether that flat per month, whether that per 3 months, or every time they are having a harvesting, they do the tariff collection. It depends on the communities. Now, yeah, just to give you a little bit overview, I think Malaysia and Indonesia share similarities on the geographical challenge, but I've been to several places, and honestly, these are very challenging areas with the very limited infrastructure. As long as you reach the eastern Indonesia, it's getting worse. So I can understand if the government have a huge task in their hand. Now, the research that I conducted is through the work with GIZ. It's called Photovoltaic Battery Mini Grid for Rural Electrification in Indonesia. It's accessible. You can download that later on. For the purpose of this presentation, I delayed much of the methodology because it's time consuming. So I'm just gonna go straight to findings and lesson learned that might be benefit to the participants. I know that majority will be engineers, so as much as possible, I will reflect on this. The first one is the technical findings. When we, sorry, I think I have, okay. When we designed the technical at the planning stage, the question that we asked is how can we design a system that can survive in the remote and also off-grid settings with very limited connectivity to harbor or even to the main cities. So the technology itself, the design, it's the result of prolonged discussions on whether adopting certain technology advancements, what we call smart system, for example, will be also followed by capacity of the operators or the community, whether they can actually operate them We consider whether they're in this local area, they have EPCs or operation and maintenance companies working that can provide service after installations, whether the warranty claims has been defined in advance to allow the community members to be able to claim them with no cost, and we calculate the gap financings. And much of this we handed over to the provincial government for purpose of budgeting. So a lot of the questions are being asked during the development, in much of that including troubleshooting, diagnosis skills, how can we provide a standard communication to these communities? So in communicating the problems with the team in Jakarta, they will use the common set of communication that we can understand. And also, how can we build a marketplace? Now, this is a huge question. We come to the conclusion that even though Indonesia already set up more than 1,000 mini grids, we haven't stimulated that mini grid market yet for several reasons, because mainly because regulatory bottlenecks. And one of the questions that also we emphasize is to make sure that all the built-in documentations are available anytime for anyone who have a capacity to repair or provide service to these community services. So these are the questions that we ask, and along 10 years of the implementation, the government of Indonesia already tried lead acid batteries, lithium batteries, and also zinc air batteries. We are able to tell which one is perfect or fits to very secluded communities, and which one that has connectivity and able to maintain lithium or smart system that we have in zinc air battery system. So these are the questions and lessons learned that we achieved. Now, from post-installation management, this is much of the issues on community, how the community manage their own installations. We do aware that strong legal establishments will allow these communities to benefit from the systems, benefit from the tariff for productivity and also economic development in their areas. So we can't let them have a group of people manage the installation. We need either cooperative or village-owned enterprise who has stronger legal establishments. And these type of legal establishment also receive funding from national government and also provincial government. And another lesson learned that we achieve is actually that these installations in some regards increase a relationship between operators and also with the community. So they have to develop a transparent system on place to be able to transparent to the community, so community knows how much money they earned and where the money goes. These will lead to strong trust between the operators and also the community, and eventually will lead to sustaining the system itself. Now, much of the issues that we tackling, we know that we're still lacking contract for inspection. So majority of the system has already been running about 10 years, and I think only about 30% of them are being inspected by local government. So this is one of the gaps that we still need to address. We need the local government to do a frequent inspection to ensure that the system is running well. Now, one of the conclusion is if all these things that we learned are not working, at least we have a universal remote monitoring system on place so that the team in Jakarta, especially in the Minister of Energy, can control the systems remotely. From impact assessment, I think this is has been heavily discussed in literatures, but I like to give another lesson learned that these mini grids not only creating businesses, also creating job, but also they have created a local economic in these remote villages. Now we have an issue with metering system because in some of the villages we have we put energy limiters, which then when we track back into the feasibility study, we realized that the feasibility study isn't strong enough to tell us that actually the load demand in this village it's bigger than what we thought. So be aware of the metering systems. Make sure to have a full understanding on the feasibility study, and then load demands are presented in a very scientific way. From the ecological and climate impacts, one of the lessons learned that we learned so far is our weak regulatory framework that we have in Indonesia in regard to waste management. So after 10 years, we do realize that this regulation hasn't been set up to fit into the needs of remote areas, because the current regulations is created to entertain the big cities needs, not the small islands or remote areas needs in terms of waste management. From social and gender impact, I think one of the lessons learned that we already highlight is from the woman itself. There is an increased sense of safety, especially because with the street light at night, it allows them to have increase their mobility at night from doing a business or even to walk around in the village. And this is important in the design because after reviewing the document, we do realize that in some of the village, when the battery systems is very low in regard to the load, they normally turn off the street lights. So the women have been complaining about street lights are not working. So this is already reflected back into our planning. May be wise to separate the street light services, probably have their own battery energy systems with the one that used by households. And another thing is the triggering more substantial productive use of energy, because with the current energy that we provide between 400 watt hour to 600 watt hour is only enough for communities to have lights at night. They normally invested in entertainment. That's going to be their first choice before they are doing a investment on productive use of energy. So in the current discussion, we also discuss about whether to separate the energy source for productive use of energy. In case of leadership, how this PV influence the social capital in the village, we find that in several areas, if the local leaders are not involved or not consulted from the beginning, they have less ownership, and normally it will lead to conflict with operators. And this normally worsened by the fact that some of the operators have a leadership skills, and they normally run for local leaders, head of the village elections, and they have more power after the winning the elections. So potential conflict also happen if operators have much power after winning the election, for example. And then the other things that we found interesting is that we don't pay attention much on educating the customers, because the EPC only have 2 to 3 months to install the PV systems, and during that time they also provide training to the operators, and they also did some community engagement with local community, but apparently it's not enough. The expectation of the local communities is the service is going to be this similar with what their fellow families in the other areas receive from utility companies. So they will invest this in some areas. They will invest it on high voltage appliance, and then they do realize that they don't have enough energy in the house. So the education part is one thing that we still need to work on it, and it's a continuous discussion between the government here in Indonesia. I think that's all from my presentation. I hope it's give a little bit clear perspective on how the mini grid in Indonesia has been established over 10 years. We have to remember that over the 10 years, the government actively developed the project, so acting as a project developer. So when you're talking about why mini grid industry is not growing in Indonesia, that's because it's mainly built by government. For more resources, you can always visit this link. I can share the presentation. Thank you very much.
Okay, thank you, Mr. Dedi, for a very interesting presentation. It was very insightful, and coming from a non-engineering background, I think this is a very interesting topic to listen to. Okay, I would like to open maybe one simple question for Mr. Dedi. I would like to invite all the participants to ask question if you have any. Okay, I guess that there is no question for Mr. Dedi. So I think without further ado, since time now is already 6:22 and we still have 3 more presenters. So maybe we can just proceed with the next presenter. The next presenter is presenter 028025, and he or she will deliver the topic of enhanced dye synthesized solar cell efficiency of titanium oxide, dope reduced graphene oxide. Okay, can this presenter raise up his hand or give any sign of attendance here? I repeat, presenter 028025.
Just raise your hand to activate your and unmute your microphone. So like Satul said, paper 028025.
Can you show us any sign of presence here? Maybe a raise of hand, or maybe you can unmute or something. Oh, okay, Dr. Sikuni. Okay. Okay, Dr. Sitikuni, the screen is now yours.
Okay.
Can you share the slide?
I share the slide with.
Okay.
Okay.
Okay, you must start the presentation, Doctor.
Okay. Can start. Can start now?
Yes, you can start now, Doctor.
Okay. Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon to all of you. Okay, today I would like to share my research project entitled Enhanced Dye Synthesized Solar Cell Efficiency of Titanium Oxide Dope Reduced Graphene Oxide. Sekejap Kenapa tak dapat ni? Okay. In 2016, around 4,316 villages that consist of 40,000 homes in rural areas Sarawak have not received electricity and still relying on expensive energy generator sets. Therefore, renewable energy is a source of electricity, and then one of the potential renewable energy is dye-synthesized solar cell, which is low cost, simple and environmentally friendly production. Okay, however, dye-synthesized solar cells still at early stages of the development cycle. It is low efficiency, which is currently the efficiency of a solar cell is only around 14%, and then it highly dependent on the synthesized dye and wide bandgap material. Okay, and then nowadays the the material of counter electrode, which is photoanode, still a matter of research to increase the efficiency of the SSC. Okay, so in our research, we investigate the material of the photoanode, which is we use titanium doped RGO, and then we study the molarity of RGO effect on the performance of the SSC. And then we also investigate the various type of dye synthesizer, which is organic dye, which are curcumin from turmeric, anthocyanin is from beetroot, and chlorophyll is from spinach. Okay, and then our aim is to determine the best molarity of RGO and synthesizer for the SSC application. Okay, so let me explain to you the experimental procedure in preparation of anode. First, we synthesize RGO by chemical reduction. We use hydrogen hydrate as agent, reduction agent, and then we prepare the glass substrate. We use the FTO, and then after that, we deposit RGO and FTO. Then extract dye synthesizer solution. After that, we prepare the electrolyte and we did the IV characteristic to measure the current and voltage and calculate the PCE of the SSC. Okay, and then at the same time, we prepare the cathode. We prepare the counter electrode by depositing graphite on the conductive side of glass by using dark lead pencil, and then we perform the measurement for structural properties. We use scanning electron microscope, whereby we have to measure the optical properties. We use the UV-Vis, and then we characterize the chemical bonding structure by using X-ray photoelectron spectroscopy, and then we measure the IV characteristic by using Keithley 2450 source meter. Okay, let me explain to you the result of this research in terms of the structural properties. Okay, so we measure the molarity dependence on the structural properties, and then the molarity is 0.05 molar, 0.010 molar, and 0.015 molar. Okay, and then we investigate the structural properties in terms of the porosity, and then we observe that the porosity between each folded layer RGO particle increase as the molarity increase. When the morphology of the RGO is more porous, it may have the higher chance to absorb high amount of sunlight. Okay, and then we enlarge the structure of the particles for 0.05, 0.010, and 0.01 molarity, and then we observe that for 0.05 molar it shows the absence of folded or crumpled structure, which indicate that the graphite is not completely oxidized. Whereby for the 010 molarity, it shows a crumpled structure, which indicate the graphite had fully oxidized by oxidizing agent. And then for 0.05 molar of graphene oxide solution, it shows fully exfoliated with the plentiful presence of crumpled and folded structure of RGO. And then we perform the optical properties measurement. We use the UV-Vis to measure the material, which is RGO. And then we observe that the absorption peak was at 259 nanometer for 0.05 molar, and then 260 nanometer for 0.010 molar, and 261 nanometer for 0.15 molarity, which correspond to the 5-to-5 transition for carbon double bonding. Okay, and then another similar shoulder was absorbed around 340, which is this area. Okay, for all sample, which shows that N-to-5 transition of the carbonyl group. Okay, which is C-double-O bond. Okay, and then RGO sample with 0.10 molar, the red color, has a high absorbance peak, which is 0.083. However, for RGO sample with 0.15 molarity, which is blue in color, has lower absorbance. Okay, this result implies that over-oxidation of RGO during doping process of 0.05 molarity. Okay, then we measure the optical property for the different dye. We measure the turmeric, which is curcumin, spinach, chlorophyll, and then beetroot is anthocyanic. Okay, we observe that the chlorophyll spinach, okay, which is blue in color, okay, shows the greatest number of absorption peak than the other dye solution. Then this result and then we expect that this chlorophyll dye have better performance for the SSC application. Okay, so after we to fabricate the SSC, we dope TiO2 GO, and then we have to characterize chemical bonding structure of this material, because we want to see whether carbon can be substituted into the TiO2 atom during the doping process. Okay, and then we observe that from the figure A, this is the survey scan. Okay, we observe that the sharp photoelectron peaks at 280 electron volt, which is C1s spectrum. And then we observe also at 450 electron volt, which is Ti2p spectrum, and then 01s electron volt, which is 01s spectrum. Whereby we also observe the peak, the unknown peak at 980 electron volt and 1100 electron volt. This peak may be due to the residue or contamination during the sample preparation. And then we investigate the each spectrum further by using the narrow scan. Okay, for the figure B, which is C1s spectrum, we observe that the three peak, which is at 284 electron volt, 286.2 electron volt, and 288.5 electron volt, which correspond to the C-double-C bond, CO, and C-double-O bond. Okay, so this C-double-O bond is actually TiOC bond. Okay, so from this result, it shows that some of titanium atom in TiO2 have been substituted by carbon atom during doping process. Okay, and then we investigate further on the titanium 2p narrow scan spectra. Okay, and then we observe that the stronger peak at 458 electron volt, and then 463.8 electron volt. Actually, this peak is due to the Ti4 plus, while weaker peak are observed at 461.7 electron volt and 459.7 electron volt. That indicate the titanium 3 plus. Okay, and then we also for the O1S spectra, we observe that two peak, which is 529.2 electron volt. Okay, and then 531 electron volt. So for 529.2 electron volt, actually this peak is OH group, where TiO2, and then 531 electron volt is OH group. Okay, so this result implies that the doping process TiO2 with RGO is performed with mixed oxide. Okay, and then we measure the IV characteristic. Okay, we compare pure titanium dioxide IV characteristic with titanium RGO DSSC, and then we observe that the current and voltage of TiO2 dope RGO, which is the red color, has higher current and voltage compared to pure TiO2. So we also calculate the PCE, and then we get 1.2% of PCE for TiO2 RGO, and then only around 0.19 for TiO2 pure TiO2 DSSC. So this result shows that doping TiO2 with RGO can improve the performance of DSSC. Okay, so now I want to conclude the research finding, my research finding. Okay, and then the increasing of the molarity affect the morphological properties of RGO. The RGO with molarity of 0.01 molar has an optimal molarity and used for the SSC fabrication. XPS analysis shows the formation of TiOC network for TiO2 with RGO, which give an improvement of the SSC efficiency. So that's all for from me. I open for the Q&A session.
Okay, thank you so much, Dr. Setikotni. And now we open thank you for your presentation and sharing this worth information. So now we open the Q&A section for the audience. So if anyone you want to ask Dr. Setikotni regarding for this topic, please type your question in the Q&A box or raise your hand to unmute your mic. Thank you. So any questions from the audience? You can type the question and I will ask for Dr. Setikotni, or you can directly ask her after you mute your mic. So I think so far no question.
Yeah.
So thank you so much, Dr. Setikotni, for the presentation. Yeah.
Okay.
Yeah, thanks so much.
Okay.
So now we move for the next presenter, which will be I think Muhammad Ashfaq, yeah, with title, yeah, with yeah, it's available. I think it's available, right? Yeah. His number of the 053051. Yes.
Hello, you can hear me right here?
Yes, I can hear you.
Okay, nice.
Yes. Please check if you can share your slide or not.
Yes, sir, yeah.
Yes, very good.
Is it visible?
I think yes, okay now.
Okay.
Yes, you can start now, yeah?
Okay.
Yeah, you have 15 minutes and 5 minutes for Q&A. Thank you so much. Okay, good luck.
So, good evening, everyone. I'm Mohammad Ashfaq, and I'll be presenting you my topic on feasibility sizing and economic analysis of solar energy system for Green Swinburne campus. Moving on. So, why implement a PV system for Swinburne? So, one of the first reasons is, of course, to combat climate change. So, we have this fossil fuel usage, and because of their depletion and, of course, their effect on the environment, it's better to move on to the renewable energy sources. And as well as the other point is the lower electricity bill. So throughout a solar PV system's lifespan, the electricity bill will be lower compared to buying it from the electricity provider. So these are the harvesting prospects in Malaysia. As you can see, this is the map of Malaysia, and Malaysia itself is actually geographically very well blessed. It's closer to the equator where you can actually harvest real good solar power here. As you can see, Kuching specifically, that's where Swinburne is. It gives around 3.5 kilowatt hour per kilowatt peak, which is actually good enough for solar energy harvesting. So these are the existing PV projects in Malaysia. Monash University already actually has its own PV system, which is around 7.36 kilowatts, uses around 115 panels, and covers an area of 110 meters squared. And another study done, similar to mine, which is a techno-economic study done by the University of Malaysia, Pahang. It's actually to see if it's feasible to implement a 1 megawatt grid, which is actually huge. And this one considers around 4,200 panels of 235 watts installed in a huge area of 20,234 meters squared. So how am I going to implement this system for Swinburne? I'll have to follow, of course, a small timeline. And that is, first of all, obtaining the data, next, sizing the PV system, and finally, doing a small economical analysis. First, obtaining the data. So first of all, I'll have to look through the solar irradiance and the temperature over the Swinburne University. Why temperature? It's because temperature actually affects the solar panel power input. So I get all of this data through PVGIS. This is an online source where you can you can access the specific locations solar irradiance data, and then you have to get the total area available. We get that through Google Maps, through the measured distance function, and then we have the load demand of Swinburne. So I'll be getting Swinburne's load demand through their own electricity meter readings, the optimal angle to harvest the solar energy, and then the temperature coefficients. Now, to size this PV system, rather than going off-grid, I'll be doing a grid-tied PV system. So off-grid is basically you're, of course, going off the grid. You're not getting electricity from an electricity provider. The reason why you didn't go off-grid is because of the battery costs, battery efficiency costs. It actually adds up a lot. So grid-tied is a little easier. And calculating the number of panels required, I'll be adding in inverters, of course, and then choosing the PV systems, PV components from the market, and calculating the temperature effect on the panels. And then for the economical analysis, I'll be doing a small life cycle cost analysis, which is basically how much would it cost for this whole PV system. And then after spending on this initial investment, by which year can we get back all of the initial investment made? So these are my results. These are the results I specified here. And see, this is the solar irradiance data. So this data is basically from 2010 to 2016. Per day, what's the average solar irradiance? So you can see there's a peak at 1 o'clock, which is the highest sunshine time, and gives around 750 watts per meter squared. This is the temperature data. And these are the temperature coefficients. So these coefficients, for example, polycrystalline silicon, for each increase in temperature, for each degree of increase in temperature, it will drop by 0.48 efficiency of the panel. And this is the power demand for Swinburne. So all of this is taken to Swinburne's electricity meter readings. And as you can see here, this is the total power consumption. So for a day, actually, Swinburne uses around average 18 megawatts an hour, 18 megawatt hours. Yeah. So first, to implement this PV system, I'll have to see, should I implement it to all of Swinburne or just one block? So as a small theoretical study, I thought maybe why not just calculate and see how much we can produce, how much PV energy we can produce with all of Swinburne's available space, even including the field here. So the total area with all of this free space available is actually is close to 12,000 meters squared. So doing a small calculation with 12,000 meters squared, the daily sunshine we get, and then of course 20%, using a 20% efficient solar panel, and assuming a 25% power loss in the system, we get around 8.4 megawatt hours. So Swinburne needs close to 18 megawatts watt hours, but we can only produce 8.4, which means I can't do it for all of Swinburne. Therefore, I chose this specific block, block E. And this is the demand for block E. So I basically went to the block E, estimated all of the components there, got the readings and all there. So the power consumption for block E comes around 472 kilowatt hours. Now we'll have to satisfy 472 kilowatt hours with the solar panels. How many solar panels do I need? This is the calculation for it. So I went through, for the components, I chose one of these panels here. This is the model number for it. It's an 18% efficient panel with a maximum power of 350 watts. So the power for one of these panels produced for a day is 1,631 watt hours. And then including the temperature effect, it drops down to 1,474. Let's assume if there's a 20% system power loss, once you connect just that panel, we get down to 1,179 watts. So this one, using this and the total energy required for a day, just a small division, you get 400 panels. And then you simply size the inverter. This is the inverter sizing equation. According to the maximum power of the panel and the number of panels, this is the inverter size. I made a small MATLAB program just to make sure, so I can add all of the panels in the market to see which one is the most efficient and which one would give. So this is, I got around 400 panels, which requires an area of 776.53 meters squared. So these are the components I plan on using for this theoretical study. So this is the 18% solar panel, the inverter here, the DC combiner box, and then this is the cable. This is an example placement of the panels. It's not that clear. And this is 100 panels in this cluster, 100 in this, 100 in this, and 100 in this. All connecting to a DC combiner box and straight to the grid. So this is the economical analysis. This is a quick breakdown here. I haven't mentioned much here because it's going to take a little long. So this is the total panel cost. This is the total electrical components cost. Wiring, you have the inverter, you have the DC combiner box. And then this is the civil. You see the mounting structure, how much would it cost for the labor. And this is the operational and maintenance, which is around 2% of the initial total capital cost. So we get to around 400,000 ringgits. And this is a life cycle cost comparison. You can see that the panel costs close to half of all of this initial capital investment for this PV system. And this is a breakdown. This is a simple breakdown. I'm not going to go through this a lot. So this is basically the panels, the cost for all of them. And this is the shipping price if you're planning on shipping all of this cargo. I got to chat with some of the dealers through AliExpress and some of those sites to get prices on these. And then you have the inverters, DC combiner boxes, the wiring, all of these. And then you have, they add up to these prices here. And then you have the operational and maintenance, which is around 2% of this initial capital cost. And yeah, so that is the total. The total basically comes around 400,000 ringgits. And now the levelized cost of energy. So this levelized cost of energy is actually how much it would cost for 1 unit of energy produced by this PV system throughout its lifetime. So as you can see here, for 20, I've considered this PV system running for 20 years. If it runs for 20 years, it generates, a unit can be bought for actually 0.1 ringgits. So each of these units generated by this PV system will cost only 0.1 ringgits. So that is the level of cost of energy. You have the so this is the other one is the feed-in tariffs. So basically, we have to cover our initial investments what we made. Since this is not an off-grid system, but we'll be feeding this directly to the grid. In West Malaysia, there is actually Sustainable Energy Development Authority, SEDA, where they provide fit rates. So this is feed-in tariffs. If you provide a unit of electricity to their grids, they will pay you back. So using their rates, we'll actually get 1.6 million in 20 years, which is around 82,000 ringgits annually. And then you have, since Sarawak Energy yet, I have to see if they provide fit rates. I assume that once we, for example, we are buying from them a unit of electricity, for example, 30 Malaysian cents, we'll be also selling it back. When we sell back a unit of electricity, they'll be giving us money for the same rate. So assuming that, but I got around 50,976 annual payment. So using this Sarawak Energy's rate and then the initial investment made, I get the payback period for around 8 years. So by the 8th year, we can cover back all of the initial investments made. and my conclusion. So I wanted to see if I can implement a full system for Swinburne, full PV system just for all of Swinburne, but it couldn't. Therefore, I chose Block Key. So Block Key's power was demand was easily met with 400 panels and 350 watts, covering just 776 meters squared. And then the panels can cover all of Block Key, as you saw before. And then payback period is exactly around 8 years. So if we run for 20 years, the remaining 12 years will be a profit margin. And yeah, that's it from me.
Okay, thank you, Mr. Mohammed, for the very interesting presentation. I would like to open the Q&A session now. Anyone have any question to Mr. Mohammed? Okay.
Is that a question over there? No. Okay.
I guess no question for the time being. So without further ado, I would like to call the last presenter, Miss Ellen Albania from UNIMAS.
Just edit into the buttons.
I edit it.
Okay.
Your name is normal.
Just continue.
Okay, Miss Eileen, the screen is yours now.
Hello?
Hello? Okay, you may start your presentation. Okay, anytime you're ready.
Hello? Hello?
Yeah, your voice is very clear here.
Okay, okay.
Okay.
Okay, good evening, everyone. So my name is Elin Albania Linus, and I'm a postgraduate student from UNIMAS. Today, I would present on my topic of development of solar power system for Sarawak pit water electrocorrelation treatment process. Moving on to the presentation outline. So the presentation is divided into 4 parts. Okay, into 4 parts: background, methodology, discussions, and also the conclusions, where it is regarding the recommendations on future work. Moving on to the background of solar power in Sarawak. Malaysia is located at the equator, where it is hot and humid throughout the year. Approximately about 22 degrees Celsius to 33 degrees Celsius of ambient temperature, with a monthly radiation of 400 to 600 megajoule per meter square. So thus made Malaysia or Sarawak also a strategic location for implementation of solar power. Okay, moving on to pit water. Malaysia has approximately of 2.6 million hectare of peatland, which is over 70% of the total peatland in Malaysia. It is located in Sarawak. Peat water is most commonly used as domestic water or for domestic usage in the rural coastal area of Sarawak. However, direct consumption of peat water is not advisable. Hence, there is a need of a treatment system to treat peat water for usage of for daily use. Okay, a little bit. Hello. Okay, a little bit of introduction regarding electrocoagulation. Electrocoagulation is an alternative for chemical coagulation process where it is capable of reducing the need for chemical coagulant. And okay, so it is capable of reducing the need of chemical coagulant since electrode is used to provide coagulant. Other than that, electrocoagulation is an environmentally friendly process. Also, it is a very economical process, easy process unlike other coagulation methods. Okay, a little bit of the objective of the study. So first is to study the solar-powered electrocoagulation system. Next is to design and fabricate the system. Third is to conduct an experimental study on the parameters in optimizing the electrocoagulation system. I would like to highlight also that this research is an early process. So the aim of the research is to investigate whether solar power is reliable or not to generate electricity in providing for electrocoagulation treatment system. Okay, moving on to the problem statement. So here there are 4 problem statements. So the first one will be the villagers in rural coastal area are currently using peat water and also rainwater for their daily usage. As shown in this picture, they are using it for washing purposes in their daily life. Other than that, the treatment of peat water by using conventional treatment system is not advisable, where during the chlorination process, it causes the formation of strong toxic. Other than that, Sarawak Alternative Rural Water Supply emphasized on a new technology which is affordable material cost, and also to highlight that 39% of the rural areas household in Sarawak have not received clean water. So hence, this problem needs to be combated by using a system which is independent and can be provided in different villages. Okay, moving on to the methodology. Methodology is divided into 3. So the first one is on the design and fabrication of solar power system, and then on the experimental study, and then on the evaluations of solar system for electrocoagulation treatment system. Okay, looking into the design and fabrication process. The design and fabrications the designs and criteria is divided into 3, which is the first one is that the material used are available readily in local market. Second, simple fabrication and maintenance process. Third, low fabrication and operating cost. Okay, for the solar power system sizing, these are the equations used. So first is the PV module sizing, and then the second would be the number of PV panels needed, and the sizing of standard charge controller, the battery capacity, the number of batteries, and also the sizing of the inverter. Okay, this is the process flow diagram of the solar power system. So it started from the energy source to the PV array, to the energy storage, and then the battery to the to the controller first, then to the energy storage system, battery to inverter, AC load, and also DC load. So there are two types of current which are needed for electrocalculation, so which is the DC load and also the AC load. DC is for the electrode, whereas the AC loads are for the pump and also for the sensors. Okay, so this is a more detailed process flow diagram of the solar powered system, and this is a picture of the configuration of the experimental configurations. So the solar panel used is a polycrystalline solar panel, and also a pure sine wave inverter, and a PWM charge controller is used. As for battery, it's the lead acid battery. Okay. So this is the two different model of electrocoagulation treatment fabricated. So this one is a batch process, whereas this one is a continuous process. So these are two different process, but two different types of process, but still electrocoagulation process. And okay, for the experimental study, the parameters for experimental study for both batch and continuous system. So for batch, we are using 2 cm electrode spacing and 8 number of electrode. And for continuous, 0.7 cm electrode spacing and 20 number of electrodes. Same amount of treated water, same treated time. So these configuration are So these configuration are investigated earlier with different experiments. Okay, for result and discussion. Okay. These are the results and discussions. So these are the results for temperature and irradiance. So for temperature and irradiance, on clear weather, irradiance will increase and the temperature will also increase. So from the result obtained, we discover that 30-degree angle shows the highest amount in terms of temperature, which is about 75 degrees Celsius. And also for 25-degree angle, it's slightly less in value, which is about 55 degrees Celsius. And also for irradiance, angle of 30 degree is to be quite consistent from 9 a.m. to 1 p.m. as compared to other angle. So with this, solar irradiance is one of the factor in determining the locations where location with high irradiance is preferred. Okay, next is on to the output parameters. So here are the output parameters for current and then for voltage output from the solar panel and also power generated by the solar panel. So also from here, it is concluded that 30-degree angle is the most better angle as compared to the other angle, and also the optimum time to harvest the solar energy is about 11 a.m. to 1 p.m. daily. Okay, this is the power output from the battery and the power input to the inverter. So the highest power output from the battery is on 1 p.m., which is at 25-degree installment, which is about 27 watts. And also the lowest power output is at 4 p.m. for 30-degree installment, which is about 23 watts. So 28 watt is the required watt for the system. So we can see that the solar power system are unable to meet the required power. Okay, so this is the power output for DC bulb, pump, and also an AC bulb. So for the AC load comprised of 5-watt AC pump and also 18-watt AC bulb. So with a total of 23 watts. And also the DC bulb is comprised of 5 watts. So as stated, for 2 p.m., the 20-degree installment is about 25.5 watts, which is the lowest, which is the highest, sorry. And for 3 p.m. is the lowest, which is 23.2 watts. So the total power generated by the AC load is 21 watts according to the collection of data. Okay, the final outcome. So as stated earlier, the main aim of this research is to see whether solar is feasible or not in using it as an alternative energy for electrocoagulation. So to compare without and with solar power. So without solar power is by using the power provided by the grid. So the removal efficiency is about 93.35% for batch and 100% for continuous system. However, for solar, it's only about 18.8% for batch and 46.15% for continuous. So it can be seen that the efficiency is quite low as compared to the with the electricity from the grid. However, it's proven that solar power is able to remove turbidity in the pit water. So hence, proper sizing of the solar power system is needed, and also further research in improving the efficiency is needed. Okay, as a conclusion to my presentation today, the 30-degree solar panel angle is the optimum angle where it absorbs the most heat and solar irradiation from sunlight. And also, solar power is feasible to be a power supply for electrocoagulation of treatment of pit water treatment. And also the system is cost effective where it can be adopted by the community. However, further research on the improvement of the solar power system is needed in the near future. Here are a list of references for my presentation today, and that is all. Thank you.
Okay, thank you so much, Ms. Ellen, for your presentation, and all the best for your next stage and next process and the implementation. So now I open the floor for the audience. If you have any questions, you can raise the hand, unmute your mic, or you can type the question in the Q&A box to ask me, Ms. Ellen. So any question, please type it or raise your hand. Audience, I think so far, I think no questions. So thank you so much, Ms. Ellen, for your presentation and this worth information, and all the best and good luck. Thank you so much. Yeah. So for all of you, for all audience, thank you so much for your attending, and we appreciate your for attending today for this section. Thank you, and all the best for you. And we'll see you tomorrow for our other section. Yeah. Thank you for everyone.